What if tomorrow the seas began to harden, the air grew sharp, and glaciers walked across continents again? This is not the stuff of nightmares, but of memory, Earth's memory, written in stone and ice, whispering that what happened before will happen again. We live in the warmth between breaths, in the pause between Earth's great inhalations of cold. And perhaps we have grown too comfortable in this fleeting summer that we call civilization. Imagine waking to find frost creeping across your windows, in patterns you've never seen before, not the delicate lacework of a winter morning, but something deeper, more purposeful, as if the cold itself were drawing blueprints across the glass. The meteorologists would speak of unusual pressure systems, of polar vortexes slipping their ancient boundaries. But you would sense something older, stirring, something that remembers when ice sheets stretched from pole to pole and the world wore white like a shroud. The signs would be subtle at first, summers that never quite arrive, winters that forget to leave. Snow falling in June across latitudes where flowers should bloom, and in the Arctic where the ice has been retreating for decades, a strange stillness as the melt suddenly stops, reverses, begins to thicken again. Scientists would measure the changes in parts per million, in degrees and decimals. But the Earth would be speaking in a language far older than numbers, the patient, inexorable grammar of deep time. We have seen this before, though not in any lifetime we can remember. 20,000 years ago, which is barely yesterday in the Earth's accounting, ice covered half of North America in sheets 2 miles thick. The weight of all that frozen water pressed the very bedrock down, reshaping continents like clay under a sculptor's thumb. Forests became tundra, tundra became nothing at all, and the great rivers of the world became ribbons of ice threading through valleys that groaned under more cold than they had ever been asked to bear. But ice ages are not catastrophes in the way we imagine catastrophes, sudden, violent, shattering. They are rhythms, as natural as breathing, as inevitable as the turning of seasons stretched across millennia. The Earth has been dancing this dance for millions of years, warming and cooling in cycles so vast that entire species rise and fall. In the spaces between steps, we think of ice ages as endings, but perhaps they are better understood as pauses, as moments when the planet gathers itself for another long exhale of warmth. The mathematics of it are written in our planet's orbit, in the slow wobble of its axis and the gentle ellipse it traces around the sun. Milutin Milankovitch saw this pattern decades ago, calculated how the Earth's dance with gravity and light creates rhythms of warmth and cold that echo across hundreds of thousands of years. When the northern hemisphere tilts just so, when summer sunlight falls at just the right angle across the vast snowfields of Canada and Siberia, the ice begins to grow. It grows slowly, season by season, century by century, until what began as snow that forgot to melt becomes glaciers that carve valleys and push boulders across continents like children moving toys. Could it happen again? The orbital mechanics that brought ice before are still turning their ancient wheels. In perhaps 50,000 years, maybe 80, the calculations suggest that northern summers will grow cool again, that snow will begin to accumulate where it has not lingered for millennia. But 50,000 years feels like forever to us, like a problem for beings so distant they might not even be human anymore. We forget that climate can shift in decades, that the great currents of ocean and air that keep us warm are more fragile than we know. There are places on Earth where you can still touch the last ice age, where rocks bear the scratches of glaciers, like scars from some ancient violence. In Central Park, the bedrock is grooved and polished smooth. Where ice once flowed like a frozen river through what would one day become Manhattan. The Great Lakes are nothing more than puddles left behind when ice sheets melted, and the rich soil of the American Midwest is ground up Canada, carried south grain by grain in the belly of glaciers that took 10,000 years to retreat. Standing in these places, running your fingers along granite carved by ice, you can feel the weight of deep time pressing against the present moment. This is what the Earth doesn't, remembers everything, records every change in stone and sediment and the slow drift of countenance. The ice ages are not history in the human sense, distant and abstract, but geology, present and pressing, written into the very ground beneath our feet. And if the ice came again, if the great cycles turned once more toward cold, what would become of us? We are a species shaped by the margins, by the narrow bands of warmth between glaciers and deserts, where life can flourish. Our cities cluster along coasts that have been stable for barely 10,000 years. Our agriculture depends on weather, patterns that are themselves young. Our entire civilization balanced on the knife's edge of a climate that has been kind to us for such a brief, bright moment in Earth's long dreaming. Perhaps we would adapt as we adapted before. Perhaps we would learn again to read the sky for signs of changing seasons, to follow the great migrations of animals toward warmth, to make tools and shelter and fire against the creeping cold. Or perhaps we would find ways to hold back the ice itself, to warm the world with our machines and our burning until even the ancient rhythms of orbit and axis bend to our will. But in the deep quiet of a winter night, when frost builds on windows and the air grows sharp enough to cut, it is worth remembering that we are small and brief, and the Earth is patient and vast, and has been practicing this dance of ice and warmth for longer than there have been words to name it. The question is not whether the ice will come again, but when, and whether we will be ready to meet it with the same quiet courage that has carried life through every winter the Earth has ever known. And in that uncertainty, in that vast and patient mystery, lies something beautiful and terrible and truther knowledge that we are part of something larger than ourselves, something that breathes in centuries and dreams in stone and remembers everything, even the things we have forgotten how to see. Ice ages are not sudden disasters, but rhythms in Earth's long breathing. Through geology and orbital cycles, we see how our planet inhales warmth and exhales cold, leaving behind scars in stone. And perhaps, as we trace these ancient patterns, we begin to understand that time itself moves differently when measured in the slow heartbeat of glaciers. The Earth breathes in cycles, so vast that human lifetimes barely register as moments between inhale and exhale. Each breath takes 100,000 years, sometimes more, and in that breathing we can read the biography of our planet, written in ice cores and ocean sediments and the patient testimony of rocks. When the Earth inhales, warmth spreads across the continents like blood through veins, forests creep toward the poles, and life flourishes in the spaces between ice. When it exhales, cold flows down from the north like water finding its level, and the world grows quiet under blankets of snow that may not melt for millennia. This breathing follows rules older than life itself, governed by the wobble and tilt of our planet as it traces its elliptical path around the sun. Every 26,000 years, the Earth's axis completes a slow gyration, like a spinning top winding down, pointing the northern hemisphere toward different stars in a cosmic dance that determines which season receives the most light. Every 41,000 years, the angle of that tilt shifts slightly, changing how directly sunlight falls on the polar regions where ice waits to advance or retreat. And every 100,000 years, the Earth's orbit stretches and contracts like a breathing lung, bringing us closer to or farther from the sun in cycles that astronomers call eccentricity, but might better be understood as the planet's way of keeping time. These are the Milankovitch cycles, named for the Serbian mathematician who first calculated their intricate choreography. But they might just as well be called the Earth's memory, because in their patient repetition lies the story of every ice age that has ever come and gone. When these cycles align just so, when orbital mechanics conspire to starve the northern summers of light, snow begins to accumulate in places where it has always melted away. 1 year becomes 10, 10 becomes 100, and slowly, so slowly, that no single generation would notice the snow compresses into ice, the ice thickens into sheets, and the sheets begin their patient march across continents. But orbital mechanics alone cannot explain the full symphony of ice and warmth that has played across our planet for the past 3 million years. The Earth's breathing is influenced by subtler rhythms, by the slow drift of continents that opens and closes ocean passages, by the rise of mountain ranges that redirect the flow of wind and water, by the chemistry of the atmosphere itself, as it swings between states of warming and cooling like a pendulum made of air and light. Carbon dioxide rises and falls in patterns that amplify the orbital signals, trapping heat when the Earth needs warmth and allowing it to escape when the planet is ready to cool. The oceans, those vast reservoirs of memory, circulate their currents in loops that can take 1,000 years to complete, carrying tropical warmth toward the poles or Arctic cold toward the equator, depending on which way the great gyres turn. In the sediments at the bottom of the sea, scientists have found the records of this breathing written in the shells of microscopic creatures that lived and died in rhythm with the changing climate. Foraminophora. They are called tiny architects that build their houses from calcium carbonate, incorporating into their walls the chemical signature of the water in which they lived. When the water was warm, the isotopes tell one story. When it was cold, they whisper another. Layer by layer, shell by shell, these almost invisible creatures have recorded every breath the Earth has taken for millions of years. And in their testimony we can read the poetry of deep time. The ice itself keeps its own records, locked in the glaciers of Greenland and Antarctica, where each year's snowfall becomes a page in an archive that stretches back nearly 1 million years. Bubbles of ancient air trapped in the ice carry samples of atmospheres long vanished, complete with their carbon dioxide concentrations, their methane levels, their traces of volcanic ash and cosmic dust. Scientists drill these cores like miners, extracting memory from the earth, pulling up cylinders of frozen time that they can read like tree rings, each layer telling the story of the year it fell as snow. And what stories they tell! Of volcanic winters when ash blocked the sun and temperatures plummeted across the globe. Of periods when the ice advanced and retreated in stuttering rhythms, as if the earth itself were uncertain which direction to breathe. Of sudden warmings, when the climate system seemed to flip like a switch, jumping from ice age to interglacial in the span of decades rather than centuries. These rapid transitions, these moments when the Earth's breathing became erratic, remind us that climate is not a gradual thing but a balance perched on the edge of chaos, capable of sudden lurches into new states that might persist for thousands of years. We live now in one of these warm pauses between breaths, in what geologists call an interglacial period, but which feels to us like the natural state of the world. The last great ice sheets retreated only 12,000 years ago, which is yesterday in geological time. And already we have built our entire civilization in the warmth they left behind. Our cities, our agriculture, our very conception of what climate should be, all of it shaped by this brief summer between ice ages. This moment of exhalation in the Earth's long breathing, but breathing by its very nature is cyclical. The same orbital mechanics that brought warmth will eventually bring cold again, and the ice that sleeps at the poles will wake and remember its ancient hunger for the continents. The question is not whether this will happen, but when and whether. We will recognize the signs when the Earth's breathing begins to shift once more toward winter. Already, some scientists suggest that our own emissions of greenhouse gases may have altered the natural rhythm, pushing back the next ice age by tens of thousands of years, or perhaps preventing it altogether. We have become a geological force ourselves, participants in the Earth's breathing, rather than merely observers of its ancient patterns. And perhaps that is as it should be. Perhaps consciousness itself is simply another variable in the planet's complex climate system, another feedback loop in the intricate dance of ice and warmth that has shaped our world for millions of years. The Earth has been breathing long before we existed and will continue long after we are gone. But for this brief moment in deep time, we are part of that breathing, part of the rhythm that connects the wobble of planets to the formation of ice sheets, to the rise and fall of species, in an endless cycle of creation and destruction and renewal. Glaciers carve valleys like patient sculptors. Each movement is measured in centuries, yet the echoes remain forever etched into cliffs and fjords. In their slow passage across the earth, these rivers of ice write poems in stone that we are only now learning to read. There is something almost alive about the way glaciers move, something that suggests intention in their slow advance across the landscape. They do not flow like water, swift and urgent, but like thick honey or cooling metal, deforming under their own immense weight at speeds that would frustrate even the most patient observer. A glacier might advance a few feet in a year, or retreat the same distance. And yet, in their glacial persistence, the very phrase captures their essence. They accomplish feats of sculpture that put human architecture to shame. Consider the fjords of Norway, those impossibly deep channels that slice into the coastline like wounds made by giants. Each one is the signature of a glacier that once flowed from the mountains to the sea, carving its path through solid bedrock with nothing more than ice and time and the accumulated weight of millennia of snowfall. The ice worked like a slow chisel, freezing into cracks in the rock and expanding with each seasonal cycle, prying apart the granite grain by grain. Where the rock was soft, the glacier carved deep. Where it was hard, the ice polished it smooth as glass, leaving behind the characteristic U-shaped valleys that geologists recognize as the fingerprints of ice. But glaciers are more than mere sculptors. They are also librarians, collecting and cataloging the landscape as they move. Every rock fragment plucked from a mountainside, every boulder carried hundreds of miles from its birthplace, every grain of sand ground from the bedrock beneath. The ice, all of it, becomes part of the glacier's cargo, its moraine, the debris field that spreads like an apron at the ice's leading edge. When the glacier finally retreats, it leaves this collection behind like a museum of the territories it has visited, a stone archive of its journeys across deep time. The Great Lakes of North America are perhaps the most spectacular example of glacial artistry on a continental scale. What we see today as Michigan and Huron, Superior and Ontario, are merely the puddles left behind when the last ice sheet melted. But what puddles they are, inland seas that contain 20% of the world's fresh surface water. The Laurentide ice sheet that carved these basins stood 2 miles thick at its center, its weight so enormous that it pressed the Earth's crust down like a thumb pushed into soft clay. Even now, thousands of years after the ice disappeared, the land is still slowly rebounding, rising at a rate of inches per century as the planet recovers from that ancient burden in the mountains. Glaciers create their own distinct vocabulary of stone. Cirques, those bowl-shaped amphitheaters carved into high peaks where glaciers are born, arates the knife-edge ridges that separate one glacial valley from another. Horns, the sharp pyramidal peaks like the Matterhorn that result when glaciers attack a mountain from all sides. Each term describes not just a landform, but a process, a way that ice and rock and time interact to create beauty that takes your breath away, even as it speaks of forces almost too vast to comprehend. The silence of glacial landscapes is profound in a way that few places on Earth can match. It is not merely the absence of sound, but the presence of something deeper, the silence of geological time itself, where centuries pass like seasons and millennia like years. Standing in a glacial valley, surrounded by walls of stone, polished, smooth by ice, you can feel that silence pressing against your eardrums, like the weight of all the years it took to carve this space from solid rock. It is the silence of patience made manifest, of forces so gradual that they redefine what it means for something to happen. Yet glaciers are not truly silent. They groan and crack and sing as they move, their ice adjusting to the stresses of flow and the changing temperatures of day and night. They calve icebergs with sounds like thunder, and their meltwater streams babble and rush with the urgent music of a world released from winter's grip. But these sounds are temporary, mere punctuation in the longer silence of glacial time. The true voice of glaciers is written in stone, in the valleys they carve and the mountains they reshape and the new landscapes they reveal when they finally retreat. The retreat itself is as much a creative act as the advance. as glaciers melt back toward their mountain sources. They reveal the valleys they have carved like an artist unveiling a sculpture. Lakes appear in the hollows the ice has gouged from bedrock. Waterfalls cascade from hanging valleys where tributary glaciers once joined the main ice stream. Forests begin their slow advance up newly revealed slopes, following the retreating ice like pilgrims approaching a shrine. But perhaps the most profound silence of glacial landscapes is the silence of absence, the quiet left behind when something immense has passed. The valleys of Alaska and Patagonia, the fjords of Greenland and Antarctica, all of them speak not just of the glaciers that carved them, but of the glaciers that are no longer there. The ice that once filled these spaces wall to wall and has now retreated to mere remnants of its former grandeur. Climate change has accelerated this retreat, turning what once took millennia into processes that unfold over decades. Glaciers that were present when our grandparents were young have vanished entirely, leaving behind only the stone record of their passage and the growing silence of their absence. In that silence, we can hear something like grief, not human grief, but geological grief, the mourning of landscapes for the ice that shaped them. But we can also hear anticipation, because glacial retreat reveals new worlds, new possibilities, new stories written in stone and waiting to be read. The silence of glacial landscapes is not empty but full, pregnant with the weight of deep time and the promise of changes yet to come. Creatures once walked across frozen plains where mammoths fell, their bones locked in ice as whispers of vanished worlds. Fossilization during the ice ages preserved not only skeletons, but tales of survival and extinction, written in bone and tooth and the careful architecture of ancient DNA. There is something miraculous about the way ice preserves the past, something that goes beyond the ordinary work of fossilization. While most ancient life comes to us as stone impressions, shadows of organisms translated into mineral Ice Age fossils arrive as if they had died yesterday. Mammoth carcasses emerge from Siberian permafrost with their fur still intact, their meat still red enough that local dogs will eat it, their DNA so well preserved that scientists can read the genetic instructions for building a creature that disappeared from the earth 10,000 years ago. The cold was both destroyer and preserver, creating conditions so harsh that entire ecosystems vanished, while simultaneously creating the perfect archive for everything that lived and died in that vanished world. In the permafrost of Alaska and Siberia, in the peat bogs of northern Europe, in the tar pits of Los Angeles, where Ice Age predators came to drink and became trapped in lakes of asphalt. The fossil record of the Pleistocene epoch reads like a bestiary from some fever dream of evolution giants and predators and grazers that make our modern world seem tame by comparison. The woolly mammoth has become the icon of Ice Age life, and perhaps deservedly so. These were creatures built for the cold, their long hair hanging in curtains to the ground, their ears small and rounded to minimize heat loss, their tusks curved in elegant spirals that could sweep snow away from the grasses beneath. They were giants in a world of giants, sharing the mammoth steppe with woolly rhinoceros that looked like living battering rams, with cave bears that stood 11 feet tall on their hind legs, with lions whose manes were adapted for hunting in the cold. and whose roars echoed across valleys that knew no human footprint. But the ice ages preserved more than charismatic megafauna. In the permafrost and frozen ground of the Arctic, paleontologists have found the delicate skeletons of Ice Age birds, the tiny bones of lemmings and voles that lived in vast numbers on the grasslands, the remains of fish that swam in lakes that have been dry for millennia. Each specimen tells part of the story of how life adapted to a world where summer was brief and winter stretched for most of the year, where the growing season was measured in weeks rather than months, and every calorie consumed had to be carefully hoarded against the return of the cold. The plant fossils are perhaps the most poignant of all leaves and seeds and pollen grains that speak of forests retreating south like armies in retreat, of grasslands expanding across regions that today know only tundra, of entire ecosystems shifting latitude with each advance and retreat of the ice. In these botanical remains, we can read the biography of the mammoth steppe, that vast grassland ecosystem that once stretched from France to Alaska and supported more large animals than any habitat in Earth's history. It was a world built on grassstuff, nutritious grasses that could grow in the brief Arctic summers and cure themselves into natural hay for the long winters, feeding herds of grazers whose hoofbeats must have thundered across the plains like perpetual storms. The preservation is so perfect in some cases that scientists can extract not just DNA but complete genomes, genetic blueprints detailed enough to resurrect these creatures if we chose to do so. The woolly mammoth genome has been sequenced multiple times, each reading revealing new details about how these animals adapted to the cold. Their hemoglobin was specially modified to release oxygen more efficiently in cold temperatures. Their skin produced a unique form of fat that remained liquid even in sub-zero weather. Their hair follicles were programmed to produce 3 different types of fur-soft undercoat for insulation, guard hairs for protection, and long outer hairs that shed water and wind. But DNA degrades even in perfect conditions, and the molecular clock that governs genetic decay means that even the best preserved mammoth specimens can only take us back a few 100,000 years before the information becomes too fragmented to read. This is the tragedy of Ice Age fossilization. It preserves so much so perfectly, but only for such recent time, geologically speaking. We have mammoth meat that is still edible and mammoth blood that can still be analyzed, but we cannot reach back to the deeper ice ages, to the creatures that lived and died in the first great glaciations millions of years ago. What we do have from those earlier ice ages comes to us in the traditional form of stone fossils. And these speak of a different world entirely. The ice ages were not a single event, but a series of them, stretched across millions of years, and each one selected 4 different survival strategies, different solutions to the problem of living in a world that oscillated between warm and cold. The earliest Ice Age fossils show us creatures that were experimenting with adaptations we can barely imagine: saber-tooth cats with canine teeth longer than carving knives, ground sloths the size of elephants, armadillos with shells like medieval armor and clubs on their tails that could shatter bone. The extinction of these Ice Age giants remains one of paleontology's great mysteries. Was it the climate, growing too warm too quickly for creatures adapted to the cold? Was it human hunting as our species spread across continents and encountered animals that had never learned to fear us? Was it disease carried by human migrants, or their domestic dogs into populations that had no immunity? Or was it simply time, the natural end of evolutionary experiments that had run their course, making way for the smaller, more adaptable creatures that would inherit the warming world? Perhaps it was all of these things at once, a perfect storm of change that no amount of adaptation could survive. The fossil record suggests that the extinctions happened quickly, in geological terms, over mere millennia, rather than millions of years. One moment, the mammoth steppe teemed with giants, and the next, it was populated by the ancestors of modern caribou and musk oxen and Arctic foxes, creatures built for survival rather than dominance. In the silence that followed, the Ice Age fossils became time capsules of worlds we can barely imagine, preserved in frozen ground and waiting for us to find them and wonder what it would have been like to share the earth with creatures so magnificent and strange. They remind us that our current world, with its particular assemblage of species and climates and possibilities, is not inevitable but contingent, one outcome among many that could have emerged from the great laboratory of ice and time. Isotopes hidden in ice cores are time capsules of breath, revealing carbon, oxygen, and dust from ancient skies. They whisper patterns of warming and cooling, cycles, both fragile and inevitable, written in a language so precise that we can read the very composition of air from thousands of years ago. Deep beneath the surface of Greenland and Antarctica, the ice remembers everything. Each layer of snow that fell and compressed into ice carries within it the chemical signature of the year it formed, complete with traces of the atmosphere that existed when that snow was still a cloud drifting across ancient skies. Scientists drill into these frozen archives with hollow bits, extracting cores of ice that they can read like the rings of an impossibly old tree. Each annual layer telling the story of the climate that created it. The isotopes are the key to this story. Atomic variations of familiar elements that act like thermometers and barometers, frozen in time. Oxygen 18 and oxygen 16, carbon 12 and carbon 13, hydrogen and deuterium. Each isotope incorporates into ice crystals at different rates depending on the temperature and humidity of the air from which the snow formed. When the climate was warm, the isotopic ratios shift in one direction. When it was cold, they shift in another. When volcanic eruptions filled the atmosphere with ash, the chemical signature appears in the ice as clearly as if someone had written a note describing the event. But the ice core reveal more than just temperature. Trapped within the crystalline structure are tiny bubbles of ancient air, perfectly preserved samples of atmospheres that existed long before humans learned to measure carbon dioxide concentrations or worry about greenhouse gases. When scientists melt these bubbles and analyze their contents, they can determine not just how much carbon dioxide was in the air hundreds of thousands of years ago, but also methane levels, nitrous oxide concentrations, and traces of other gases that influenced the climate of the distant past. The story these isotopes tell is one of remarkable sensitivity, of a climate system that responds to changes so subtle they seem almost mystical. A slight shift in the Earth's orbit around the Sun, a variation of just a few percentage points in the amount of summer sunlight reaching the northern ice sheets, and the entire planet begins to slip toward glaciation. The isotope record shows how these orbital changes triggered feedbacks that amplified the initial cooling. More ice reflected more sunlight back to space, reducing temperatures further. Less plant growth meant less carbon dioxide absorbed from the atmosphere, but also less methane produced by wetlands and forests, creating a complex dance of atmospheric chemistry that either pushed the world toward warming or cooling, depending on which feedbacks dominated. The precision is breathtaking. In the most detailed ice core, scientists can resolve changes that occurred over individual years, sometimes even individual seasons. They can see the signature of massive volcanic eruptions that cooled the planet for decades, the chemical traces of forest fires that burned across entire continents, the isotopic evidence of sudden droughts or periods of unusual rainfall. During the transition periods between ice ages and interglacials, the cores reveal climate changes that happened with shocking rapidity shifts from glacial to warm conditions in as little as a decade. Transformations so quick that a single human lifetime could witness the complete reorganization of regional weather patterns. Perhaps most remarkably, the isotopes reveal how interconnected the global climate system truly is. Changes that began in the North Atlantic appear in ice core from Antarctica within decades, carried there by atmospheric and oceanic currents that link the poles in an intricate dance of heat exchange. When the great ice sheets of North America began to melt, the isotopes show how the resulting changes in ocean circulation affected monsoon patterns in Asia, rainfall in Africa, and temperatures in regions thousands of miles from the nearest glacier. The ice core also preserved the dust of ancient worlds, microscopic particles that traveled thousands of miles on the wind before settling into the growing ice sheet. During glacial periods, when much of the world's vegetation had retreated, and vast areas of exposed ground lay vulnerable to erosion, the atmosphere carried enormous quantities of dust. The isotopes in this dust tell stories of continental-scale changes they reveal when the Sahara was wetter and greener than it is today, when the steppes of Asia were so dry that dust storms could be seen from space, when volcanic eruptions on one continent deposited ash on ice sheets on another. But reading the isotopic record is like trying to understand a language that uses the same words to mean different things in different contexts. The same isotopic signature can result from different climate processes, and the same climate change can produce different isotopic responses depending on local conditions. Scientists have spent decades learning to decode these signals, comparing ice core records with other climate archives. Tree rings and lake sediments and coral reefs to build a comprehensive picture of how the climate system has behaved over hundreds of millennia. What emerges from this detective work is a portrait of climate as something far more dynamic and responsive than we might expect. The isotopes reveal a system that can remain stable for thousands of years and then flip suddenly into a completely different state, like a switch being thrown. They show periods when the climate oscillated rapidly between warm and cold conditions, as if the Earth itself were unable to decide which state to settle into. They document times when regional climates became completely decoupled from global patterns, when ice sheets advanced in some regions while retreating in others, when the normal relationships between temperature and precipitation broke down entirely. The most recent 20,000 years of isotopic record tell the story of the world's emergence from the last ice age, but they also reveal how precarious our current climate stability really is. The warm Holocene period in which human civilization developed appears in the ice core as an unusually stable interval, characterized by isotopic values that vary much less than they did during the glacial period. This stability may be one of the reasons our species was able to develop agriculture and cities and all the other foundations of complex society. We had the good fortune to evolve during one of the calmest periods in the Earth's climate history. But even within this stable period, the isotopes record disruptions that remind us how quickly things can change. The medieval warm period and the Little Ice Age both appear clearly in the most recent ice core layers, along with the chemical signatures of major volcanic eruptions and the beginning of what scientists now call the Anthropocene, the period when human activities began to alter the isotopic composition of the atmosphere itself. Now, as we add our own signatures to the isotopic record through fossil fuel burning and land use changes, we are participating in the same processes that the ice cores have been documenting for hundreds of thousands of years. The isotopes will record our presence in the Earth's climate system just as faithfully as they recorded the advance and retreat of ice sheets, the eruption of volcanoes, and all the other forces that have shaped our planet's climate throughout deep time. Future scientists drilling ice core will find the chemical signature of our civilization preserved in the ice, a layer of altered atmospheric chemistry that marks the moment when one species learned to change the composition of the air itself. During the ice ages, water retreated from coasts, exposing land bridges that connected continents. These hidden highways of migration may hold secrets about how humans spread across Earth, but they also reveal how dramatically our planet can transform when vast quantities of water change from liquid to solid and back again. Imagine the ocean falling like a tide that never turns, dropping not inches but hundreds of feet, revealing landscapes that have been submerged for millennia. This is what happened during the Great Glaciations, when so much water was locked up in ice sheets that sea levels dropped by more than 400 feet below where they stand today. Vast areas of what we now call the continental shelf emerged. From the waves like sleeping giants awakening, creating new lands that connected islands to mainlands, and mainlands to each other across passages that had been barriers for millions of years. The Bering Land Bridge is perhaps the most famous of these drowned highways, the broad plain that once connected Asia and North America, where now the Bering Strait carries Arctic waters between the continents. But this was no narrow causeway, its greatest extent. Beringia was a subcontinent unto itself, stretching nearly 1,000 miles from north to south, covered with the same mammoth steppe grasslands that supported vast herds of Ice Age megafauna. It was across this vanished landscape that the first humans walked into the Americas, following game trails and river valleys, through a world that exists now only in the genetic memories of the species that traversed it. But Beringia was just one of many land bridges that appeared when the oceans fell. Between Britain and continental Europe, the Doggerland Plain emerged from the North Sea. creating a landscape of rivers and hills and forests where fishing boats now trawl for cod. Archaeological evidence suggests that this was some of the richest hunting and gathering territory in Ice Age Europe, supporting human populations that may have numbered in the tens of thousands. When the ice began to melt and the waters began to rise, these people faced a choice that would echo through their descendants. DNA retreat to higher ground or learn to live with the encroaching sea. In Southeast Asia, the falling ocean revealed the Sunda Shelf, connecting the Indonesian archipelago into a single landmass and creating a superhighway for the migration of both animals and early humans. The deep waters that separate Asia from Australia, the biogeographical boundary that Alfred Russel Wallace identified as one of the most significant divisions in the natural world, remained unbridged even at the lowest sea levels. But the water gap was much narrower than it is today. The first Australians must have made this crossing by boat or raft, but they were island hopping across a chain of lands that stood much higher above the waves than they do now. The exposure of these continental shelves created not just highways, but entire new worlds, complete ecosystems that flourished on the emerged land only to vanish again when the ice melted and the waters returned. Rivers that had carved their valleys during earlier high stands of sea level suddenly found themselves flowing across vast exposed plains, extending themselves hundreds of miles seaward to reach the retreated ocean. The Amazon, the Mississippi, the Hudson, all of these great rivers once had mouths that lay far from their present positions, and their ancient channels are still visible on sonar maps of the sea floor, preserved like fossil rivers carved into the continental shelf. These drowned river valleys tell stories of dramatic change that happened far too quickly for the landscape to adapt gradually. When the ice sheets began to melt at the end of the last glaciation, sea levels didn't rise smoothly, but in pulses, sudden jumps that could add dozens of feet to ocean heights in the span of centuries. Meltwater pulse 1A, as scientists call one particularly dramatic episode about 14,000 years ago, raised sea levels by more than 50 feet in less than 500 years. Any human settlements on the exposed continental shelves would have been forced to retreat inland generation by generation, watching their ancestral territories disappear beneath the waves. The archaeological implications are staggering. If early human populations followed the same patterns as other species and concentrated along coastlines and river mouths, the richest and most productive habitats available, then much of the evidence for Ice Age human occupation may now lie beneath hundreds of feet of ocean water. The earliest cities, the first agricultural experiments, the development of complex technologies and social systems, all of it may have happened on landscapes that are now drowned, their archaeological traces scattered across the sea floor or buried under millennia of marine sediments. Recent underwater archaeology has begun to glimpse these lost worlds. Off the coast of the Gulf of Mexico, researchers have found the bones of mastodons and giant ground sloths in association with what appear to be human tools, preserved in sinkholes that were dry caves during the Ice Age. In the Mediterranean, divers have discovered submerged caves with evidence of human occupation dating back tens of thousands of years. Along the coasts of Australia and the Americas, indigenous oral traditions speak of times when the ocean was far from where it is now, when ancestors walked across lands that are now beneath the waves. But the rising oceans didn't just drown archaeological sites, they may have drowned entire chapters of human cultural evolution. The development of navigation, boat building, and maritime trade may have begun much earlier than we imagine, driven by the necessity of maintaining connections across increasingly water-dominated landscapes. The first farmers may have been refugees from rising seas, forced to develop agriculture as they retreated to less productive inland territories. The myths and legends that appear in cultures around the world, stories of great floods, of lost paradises, of lands beneath the waves, may be cultural memories of the great drowning that ended the Ice Age. The speed of these changes challenges our assumptions about how human societies adapt to environmental transformation. We imagine adaptation as something gradual, playing out over many generations. But the end of the Ice Age compressed dramatic environmental changes into timescales that individual humans could witness. A person born when the ice sheets were at their maximum extent might have lived to see the ocean rise by hundreds of feet, entire ecosystems disappear, and vast new landscapes emerge from the melting ice. The social and cultural transformations required to cope with such changes must have been correspondingly rapid and dramatic. Now, as we face the possibility of renewed sea level rise driven by anthropogenic climate change, the drowned landscapes of the Ice Age offer both warning and perspective. The Ice Age sea level changes were natural processes, driven by orbital cycles and ice sheet dynamics that operated over thousands of years. But they remind us that the current position of the shoreline is not permanent, that the geography we take for granted is contingent and temporary. The continental shelves that emerged during the ice ages are still there beneath the waves, waiting. If enough ice melts, they will be submerged even deeper than they are today. If a new ice age comes, they will emerge again, creating new lands and new possibilities for whatever species inherit the earth. The ocean's memory is long, and in its rise and fall lies a story of constant change, of landscapes that appear and disappear like dreams, of species and civilizations that must learn to dance with the rhythm of ice and water or risk being swept away by forces larger than themselves. Speculation arises. Did people once build along those vanished shorelines, now drowned beneath rising seas? The ice ages conceal not just ice, but perhaps entire chapters of human memory. Civilizations that flourished when the ocean stood hundreds of feet lower and continents were joined by bridges of dry land. There is something haunting about the possibility that we are not the first to build cities, not the first to develop complex societies, not the first to believe that our civilization represents the pinnacle of human achievement. The drowned continental shelves hold more than the bones of mastodons and the fossilized pollen of Ice Age plants. They may hold the ruins of human settlements that predate our written history by thousands of years, entire cultures that rose and fell during the long cold millennia when so much of the Earth's water was locked away in ice. Consider the numbers, the vast scales of time and geography involved. The last ice age reached its maximum extent 20,000 years ago, but it was preceded by dozens of other glaciations stretching back millions of years. Each time the ice advanced, the oceans fell. Each time it retreated, again drowning whatever had been built on the exposed land. If humans or their ancestors were present during these earlier cycles, and the archaeological evidence suggests they were, then we must consider the possibility that the pattern of rise and fall has played out many times before each cycle, erasing the evidence of the previous one beneath hundreds of feet of ocean water. The younger driest period, that sudden return to near glacial conditions that occurred just as the world was warming out of the last ice age, offers a particularly intriguing case study. For more than 1,000 years, from roughly 12,900 to 11,700 years ago, global temperatures plummeted back toward ice age levels. Sea levels, which had been rising as the great ice sheets melted, stabilized, or even fell slightly during this cold snap. If human populations had been adapting to the gradually rising seas by moving their settlements ever higher up the continental slopes, the younger Dryas would have given them 1,000 years of stable or even slightly lower sea levels, enough time to establish substantial communities on what we now know was temporarily exposed land. When the younger Dryas ended and warming resumed, it did so with shocking rapidity. Ice cores show that temperatures in the North Atlantic region rose by as much as 15 degrees Fahrenheit in the span of a decade. The ice sheets, which had been stable or even advancing during the cold period, suddenly began to collapse, sending enormous volumes of meltwater into the oceans. Any settlements that had been established on the temporarily exposed shelves would have faced the same choice that has confronted coastal communities throughout history: retreat to higher ground or be swallowed by the rising waters. The archaeological evidence for pre-flood civilizations is necessarily sparse. Underwater archaeology is difficult and expensive, and most of the continental shelf remains unexplored. But tantalizing hints continue to emerge. Off the coast of India, marine archaeologists have found what appeared to be the remains of submerged structures dating back thousands of years. In the Mediterranean, underwater excavations have revealed evidence of human occupation in caves that were above sea level during the Ice Age, but are now deep beneath the waves. Along the coasts of the Americas, indigenous oral traditions preserve detailed accounts of lands that were once above water, complete with descriptions of landmarks and settlements that now lie beneath the sea. Perhaps most intriguingly, many of these traditions share common elements: stories of advanced civilizations that were destroyed by rising waters, of survivors who preserved ancient knowledge and passed it down through oral tradition, of technological achievements that were lost when the old world drowned. The flood myths that appear in cultures around the globe, from the biblical account of Noah to the Mesopotamian epic of Gilgamesh, to the stories told by indigenous peoples in Australia and the Americas, may not be myths at all, but cultural memories of real events, the collective trauma of communities forced to abandon their ancestral homes to the rising seas. The implications extend beyond archaeology into the realm of human cultural evolution. If complex societies did exist on the exposed continental shelves during the Ice Age, then our understanding of how civilization developed may be fundamentally incomplete. The transition from hunter-gatherer societies to agricultural communities, the development of writing and metallurgy, and monumental architecture, all of these innovations that we consider the hallmarks of civilization, may have occurred much earlier than we imagine, only to be lost when the ice melted and the waters rose. This possibility forces us to reconsider what we mean by progress, by cultural development, by the march of human civilization through time. Instead of a steady upward trajectory from primitive beginnings to our current state of technological sophistication, human history may be more cyclical, marked by periods of advancement followed by collapse and renewal. The civilizations that may lie beneath the waves remind us that knowledge can be lost as well as gained, that entire ways of life can vanish without a trace, that the archaeological record we rely on to understand our past may be missing its most important chapters. But speculation about drowned civilizations also raises profound questions about the nature of cultural memory and the transmission of knowledge across vast spans of time. If the flood myths and oral traditions do preserve memories of Ice Age settlements, then they represent an unbroken chain of cultural transmission stretching back more than 10,000 years. The possibility that human communities maintained detailed knowledge of drowned landscapes and lost civilizations through nothing more than stories passed from generation to generation speaks to the power of oral tradition and the resilience of human memory. Modern technology is beginning to open new windows into these drowned worlds. Side-scan, sonar, and multi-beam bathymetry can map the seafloor in unprecedented detail, revealing features that may be natural geological formations or the remnants of human construction. Autonomous underwater vehicles can explore depths that are beyond the reach of human divers, equipped with cameras and sensors that can document whatever evidence of past human occupation may have survived the millennia beneath the waves. Yet, even as we develop new tools for exploring the continental shelves, we must acknowledge that much of the evidence may be irretrievably lost. The same processes that preserve organic material in the frozen soils of the Arctic work against preservation in marine environments. Salt water corrodes metal, currents scatter artifacts, and marine organisms colonize and eventually destroy most organic materials. Any civilizations that may have existed on the Ice Age shelves would have had to build in stone to leave traces that could survive 10,000 years beneath the sea. The search for drowned civilizations is ultimately a search for ourselves, for the deep roots of human culture and the full scope of our species' achievements and failures. Whether or not we find ruins beneath the waves, the possibility of their existence changes how we think about our place in the long story of human civilization. We are not the first to face the challenge of rising seas, not the first to watch our world transform around us, not the first to wonder whether future generations will remember what we have built, or whether it too will be swallowed by forces beyond our control. In the end, the greatest treasure that may lie hidden on the drowned continental shelves is not gold or artifacts, but perspective. The humbling recognition that human civilizations rise and fall like tides, that our current moment of apparent mastery over the natural world is temporary, and that the ocean holds secrets we are only beginning to imagine. Imagine standing on a glacier where every sound is swallowed by snow. Ice is not lifeless, it groans, shifts, and records time in silence. What might silence itself be trying to tell us about the deep patience required to understand a world that measures change in millennia rather than moments? The silence of ice is unlike any other silence on Earth. It is not the absence of sound, but the presence of something more profound, the accumulated quiet of centuries, the compressed stillness of winters that lasted for thousands of years. When you stand on a glacier, surrounded by walls of ice that may have been forming since before your civilization began, you can feel that silence pressing against your eardrums, like the weight of all the years that have passed while this ice was slowly accumulating, grain by grain, storm by storm, century by century. But glacial silence is not complete silence. Listen carefully, and you can hear the ice speaking in its own language, the deep groans and cracks that echo through the glacier as it adjusts to its own immense weight. The sharp reports like gunshots when stress fractures split the ice, the musical tinkling of meltwater finding its way through hidden channels deep within the frozen mass. These are the sounds of geological time made audible, the voice of processes so slow that they usually occur below the threshold of human perception. Scientists have learned to listen to these sounds, to decode the messages that glaciers send through their acoustic signatures. Each crack and groan carries information about the stresses within the ice, the rate at which the glacier is moving, the presence of hidden crevasses or streams. Seismometers placed on glaciers detect vibrations too subtle for human ears, the whisper of ice crystals sliding past each other, the rumble of the glacier's base grinding against bedrock, the distant thunder of icebergs calving into the sea. Perhaps, most remarkably, glaciers record their own history in the very structure of their silence. Each layer of ice preserves not just the chemical composition of ancient atmospheres, but also the sounds of the world in which that ice formed. Volcanic ash trapped in ice cores carries the acoustic signature of the eruptions that produced it, the sudden violence of explosions that would have been heard around the world. Dust layers speak of continental-scale dust storms, their intensity recorded in the density of particles preserved in the ice. Even the bubbles of ancient air trapped in glacier ice carry information about the atmospheric conditions that existed when that air was first incorporated into falling snow. The silence of glaciers extends beyond sound into the realm of time itself. Standing on ice that formed centuries or millennia ago, you are surrounded by frozen time, by water molecules that last felt the touch of sunlight when the world was younger and different. The ice beneath your feet may have formed during the medieval warm period when Vikings sailed to Greenland and vineyards flourished in England. The ice deeper down may date to the Little Ice Age, when the Thames froze solid and crop failures triggered famines across Europe. At the bottom of the deepest glaciers, the ice is older than human civilization, older than agriculture, older than the last great extinction that swept the Ice Age megafauna from the earth. This temporal silence is profound in ways that challenge human understanding. We are creatures of the moment, adapted to respond to changes that occur within our lifespans, or at most within the memory of our communities. But glaciers operate on timescales that dwarf human experience, accumulating and releasing water in cycles that span centuries or millennia. A glacier that advances today may be responding to snowfall patterns that were established decades ago. A glacier that retreats may be releasing ice that formed before any living human was born. The weight of this temporal silence presses down on more than just the ice itself. Glaciers are so massive that they literally bend the earth beneath them. depressing the underlying bedrock by hundreds or even thousands of feet. When glaciers retreat, the land slowly rebounds, rising at rates that can be measured, but that occur too slowly for direct observation. This process, called isostatic rebound, continues for thousands of years after the ice has disappeared, the Earth's crust gradually recovering from the weight it once carried. But perhaps the most profound aspect of glacial silence is its capacity to make us aware of our own noise, our own restless urgency in a world that operates on geological timescales. Modern life is filled with sound, the constant hum of machinery, the chatter of electronic communications, the rush of traffic, and the buzz of activity that defines human civilization. Against this background of noise, the silence of glaciers offers something increasingly rare: the opportunity to experience stillness at a scale that puts human activity into perspective. This silence is not empty, but full of meaning, pregnant with the accumulated history of climate and atmosphere, and the slow dance of ice and rock that has shaped our planet for millions of years. In that silence, we can begin to understand something of the patience required to comprehend geological processes, the deep time perspective that sees mountains rise and fall, continents drift and collide, species evolve and go extinct in the context of changes so gradual that they require a different kind of attention than we are accustomed to giving. The silence of glaciers also carries warnings about the fragility of the conditions that create and maintain such silence. As global temperatures rise and glaciers retreat at accelerating rates, the acoustic landscape of polar regions is changing. Where once there was the deep quiet of stable ice, now there are increasingly frequent sounds of melting and collapse, rush of meltwater streams, the crack of calving icebergs, the groan of ice sheets adjusting to rapid changes in their mass and stability. Climate scientists have begun to use these changing acoustic signatures as indicators of glacial health, listening to the ice to understand how quickly it is changing and what those changes might mean for sea level rise and global climate patterns. The silence that once characterized stable glaciers is being replaced by the sounds of transformation, the acoustic signature of a cryosphere in rapid transition. Yet even as the ancient silence breaks down, it continues to teach us about the nature of time and change, and the relationship between human activity and the larger systems that govern our planet. The silence of glaciers reminds us that the Earth operates on time scales that dwarf human experience, that the stability we take for granted is temporary, and that the greatest changes often occur so slowly that they are invisible except to those who know how to listen to the deep quiet of geological time. In that silence, we can hear something like wisdom, the patience of ice, the persistence of slow processes, the quiet strength required to build mountains grain by grain and carve valleys drop by drop. It is a silence that invites contemplation, that demands we slow down and pay attention to changes that occur below the threshold of ordinary perception, that reminds us we are part of something much larger and slower and more permanent than the brief span of our individual lives. Ice ages are entropy written in frozen form systems, breaking down, energy spreading thin, life adapting to scarcity. Yet within entropy lies order, new species, new paths. new balances emerging from the apparent chaos of a world growing cold. There is a paradox at the heart of ice ages that speaks to one of the fundamental principles governing our universe. As the Earth grows cold and vast ice sheets spread across continents, we might expect to see increasing disorder, the breakdown of complex systems, the triumph of entropy over organization. Instead, we find something more subtle and strange, a world where entropy and order dance together in intricate patterns, where the apparent simplification of Ice Age landscapes conceals new forms of complexity emerging from the constraints of cold. Entropy, in its classical thermodynamic sense, is the tendency of energy to disperse, of hot things to cool down, of organized systems to gradually decay into disorder. When the Earth enters an ice age, this process seems to accelerate. Heat that once circulated freely through the atmosphere becomes trapped in ice sheets that reflect sunlight back to space. Ocean currents that carried warm water to polar regions slow or shut down entirely as the temperature gradients that drive them weaken. Forests retreat toward the equator, leaving behind simplified ecosystems dominated by grasses and hardy shrubs that can survive the shortened growing seasons and harsh winters. But look more closely, and a different picture emerges. The ice sheets themselves are marvels of organization, crystalline structures where individual water molecules arrange themselves in hexagonal patterns that repeat across millions of cubic miles of frozen water. Each snowflake that adds to the growing ice carries within its structure the same geometric principles that govern the formation of crystals and the folding of proteins and the spiral arms of galaxies. The ice sheet as a whole behaves like a single massive organism, flowing and deforming in response to its own weight, developing its own weather systems and creating its own microclimates in the zones where ice meets rock and air. The apparent simplification of Ice Age ecosystems also conceals new forms of complexity. The mammoth steppe that stretched across much of the northern hemisphere during glacial periods supported more large animal biomass than any ecosystem in Earth's history. This was not a desolate wasteland, but a grassland so productive that it could feed herds of megafauna whose migrations must have resembled the great wildlife spectacles of modern Africa, magnified by orders of magnitude. The relationships between predators and prey, between grazers and grasses, between large herbivores and the soils they fertilized, created webs of ecological connection that we are only beginning to understand through the fossil record. The constraints imposed by Ice Age climates also drove evolutionary innovation in directions that would have been impossible under warmer conditions. The woolly mammoth's adaptation to cold, from its dense fur and small ears to its specialized hemoglobin and subcutaneous fat layers, represents a solution to the thermodynamic challenges of maintaining a large body temperature in an environment where heat is constantly leaking away to the surrounding air. Cave bears developed hibernation strategies that allowed them to survive winters that lasted for most of the year. Ice Age humans invented technologies, fire, clothing, shelter construction that effectively extended their physiological capabilities, allowing a tropical species to colonize Arctic environments. But perhaps the most profound example of order emerging from apparent entropy lies in the Ice Age cycles themselves. What appears to be random oscillation between warm and cold periods is actually a complex dance choreographed by orbital mechanics, solar cycles, and feedback loops between ice sheets, oceans, and atmosphere. The Milankovitch cycles that govern Ice Age timing operate with clockwork precision across hundreds of thousands of years. Their mathematical relationships as elegant as any equation in physics. The ice ages are not chaos but pattern, not breakdown but rhythm, not entropy but a different kind of order operating on timescales too vast for easy human comprehension. The ice core that preserve records of past climates reveal this hidden order in stunning detail. Volcanic activity, solar radiation, ice sheet dynamics, ocean circulation, and biological processes. When scientists analyze these layers, they find not random noise, but signals, correlations, patterns that speak of a climate system that is sensitive and responsive and organized in ways that emerge only when viewed across appropriate scales of time and space. Even the process of fossilization during ice ages demonstrates how entropy and order interweave. The cold that killed Ice Age creatures also preserved them, creating conditions where organic material could be maintained for tens of thousands of years without significant decay. The permafrost that formed during glacial periods became a vast library of genetic information, storing DNA sequences in conditions so stable that scientists can now read the genetic instructions for building mammoths and cave bears and giant ground sloths. Death became preservation, ending became beginning, entropy became information. The relationship between entropy and order in Ice Age systems also illuminates something important about resilience and adaptation. Systems that appear to be failing or breaking down may actually be reorganizing themselves at deeper levels, finding new configurations that allow them to persist under changed conditions. The retreat of forests during ice ages was not simply destruction, but reorganization. Forest species persisted in refugia, small pockets of suitable habitat where they maintained their genetic diversity and waited for conditions to improve. When the ice finally retreated, these refugial populations expanded rapidly back into their former ranges, carrying with them the accumulated genetic variations that had allowed them to survive the cold millennia. Ice Age humans demonstrated this same principle on a cultural level. Social organization and environmental management that laid the foundation for later civilizations. The scarcity of resources during glacial periods led to more efficient hunting techniques, more effective food preservation methods, more sophisticated understanding of seasonal patterns and animal behavior. Entropy at one scale became order. At another, breakdown in some systems enabled breakthrough in others. This perspective on ice ages as expressions of entropy and order has implications that extend far beyond paleoclimatology. It suggests that apparent chaos may conceal deeper patterns, that breakdown and reorganization are often two faces of the same process, that the second law of thermodynamics does not preclude the emergence of complex, organized systems, but actually enables new forms of order to arise from the constraints imposed by energy limitations. As we face our own period of rapid environmental change, the Ice Age record offers both warning and hope. It warns us that complex systems can collapse quickly, when pushed beyond their limits, that the order we take for granted is contingent and fragile. But it also suggests that collapse is not necessarily the end of the story, that new forms of organization can emerge from apparent chaos, that entropy and order are partners in an ongoing dance of destruction and creation that has been shaping our planet for billions of years. The ice ages remind us that we live in a universe where order emerges from disorder, where complexity arises from constraint, where the deepest patterns reveal themselves only to those patient enough to observe, processes that unfold across scales of time and space that dwarf human experience. In the white silence of glacial landscapes, entropy writes its equations in ice and snow, while order responds with the crystalline geometry of snowflakes and the elegant mathematics of orbital cycles and the intricate choreography of ecosystems, adapting to the rhythm of freeze and thaw that governs the long breathing of our living planet. During glacial maximums, winds carried vast sheets of dust across continents. Each particle, a grain of forgotten deserts, settled into soils that would later feed civilizations. In this cosmic recycling of stone and sand lies a story of connection that links the rise of ice sheets to the fertility of distant valleys. The dust that fills the air during ice ages is more than mere grit blown by wind. It is the migration of entire landscapes, the dissolution of mountains grain by grain, the slow redistribution of continents carried on currents of air that circled the globe like rivers in the sky. When vast areas of vegetation retreated before advancing ice sheets, they left behind exposed soil and sediment that had been protected by root systems and leaf cover for thousands of years. Suddenly vulnerable to wind and weather, this material began its journey into the atmosphere, becoming part of dust storms that could darken skies across entire hemispheres. The scale of this atmospheric transport during glacial periods was almost incomprehensible. Satellite images would have shown plumes of dust streaming off the edges of continents, carried by trade winds and jet streams across oceans and mountain ranges to settle in places thousands of miles from their origin. Dust from the Sahara fell on ice sheets in Greenland, sediments from Central Asia. The grinding action of glaciers themselves added to this aerial cargo, producing vast quantities of rock flour-fine particles of stone ground to powder by the immense weight and pressure of moving ice. This dust was not randomly distributed, but followed patterns as regular and predictable as ocean currents, governed by the same atmospheric circulation that brings monsoons to India and hurricanes to the Atlantic. During glacial periods, when temperature gradients between ice sheets and warmer regions were much steeper than they are today, these circulation patterns were more intense and consistent, creating superhighways of dust transport that operated for thousands of years with remarkable stability. The Chinese Loess deposits provide perhaps the most spectacular example of this Ice Age dust transport system. Across vast areas of northern China, wind-blown sediments from the expanding deserts of Central Asia accumulated in layers that now stand hundreds of feet thick, creating some of the most fertile agricultural land on Earth. Each layer in these deposits tells the story of a particular climatic episode, periods when dust storms were more frequent and intense, times when the source regions were drier or the winds stronger, moments when volcanic eruptions added their own contributions to the atmospheric load of particles. Reading these dust deposits is like reading the Earth's respiratory system, preserved in stone. Each grain carries isotopic signatures that identify its source, region, chemical fingerprints that reveal the geology of landscapes that may be thousands of miles away. Scientists can trace individual dust storms across continents and through time, mapping the ancient wind patterns that connected distant parts of the Earth in ways that are invisible to us today, but that shaped the very soil beneath our feet. But dust transport during ice ages was not merely erosion, it was also creation, a process by which nutrients and minerals were redistributed from regions where they were abundant to places where they were needed. The fertile soils of the American Midwest owe much of their richness to dust blown from the Colorado Plateau and the high plains during glacial periods. The Amazon rainforest, surprisingly, depends on dust from the Sahara Desert carried across the Atlantic by trade winds and deposited in tropical soils that would otherwise be leached of nutrients by heavy rainfall. This transcontinental fertilization operated on a scale that dwarfs any human agricultural system. The dust storms of ice ages moved billions of tons of mineral-rich sediments across the globe each year, creating a planetary circulation of nutrients that connected the fertility of one region to the erosion of another. When ice sheets advanced and vegetation retreated, the exposed land surfaces became quarries from which the atmosphere extracted the raw materials for soil formation. Thousands of miles away, the biological implications of this dust transport were profound. Many of the world's most productive agricultural regions are built on sediments that were transported and deposited during ice ages. Their fertility, a direct consequence of the cold periods that seem so antithetical to life. The Great Plains of North America, the Pampas of Argentina, the steppes of Eurasia, of these grasslands that supported vast herds of grazing animals and later became the breadbaskets of human civilization, owe their existence to the dust. Storms that raged during glacial periods. The dust also carried more than minerals, it carried life itself. Microorganisms, spores, seeds, and genetic material traveled on dust particles across continents, creating opportunities for biological exchange that would have been impossible through other means of transport. The dust storms of ice ages were inadvertent migration corridors for microscopic life, connecting ecosystems in ways that influenced the evolution and distribution of species across vast distances. In ice core from Greenland and Antarctica, this atmospheric dust appears as layers of sediment that chronicle the intensity and frequency of dust storms throughout the ice age cycles. During glacial maximums, the dust levels in these cores increase dramatically, sometimes by orders of magnitude compared to interglacial periods. The chemical composition of this dust tells stories of changing wind patterns, shifting source regions, and the rise and fall of dust-producing landscapes as climate oscillated between warm and cold states. The end of each ice age brought dramatic changes to these dust transport systems. As ice sheets retreated and vegetation recolonized previously barren landscapes, the sources of atmospheric dust diminished. Root systems began to stabilize soils that had been exposed for millennia. Forests and grasslands created surface roughness that reduced wind speeds and trapped particles before they could become airborne. The great dust highways of the ice ages gradually shut down, replaced by the more modest dust transport patterns we see today. But the legacy of Ice Age dust remains, written in the landscape. The fertility that fed the agricultural revolutions of the Holocene, the soils that support billions of people today, the very ground beneath our cities and farms, much of it is dust that traveled thousands of miles on Ice Age winds, a gift from distant mountains and deserts to the valleys and plains where human civilization would eventually flourish. Now, as human activities create new sources of atmospheric dust and alter the landscapes that once captured and stabilized wind-blown sediments, we are inadvertently recreating some aspects of Ice Age dust transport. Desertification, deforestation, and intensive agriculture have increased the amount of material available for wind transport in many regions. Climate change is altering the wind patterns that govern where this dust travels and where it settles. We are becoming participants in the same planetary circulation of sediments that operated during the ice ages, though perhaps without fully understanding the long-term consequences of our participation. The dust on Ice Age winds reminds us that the Earth operates as an integrated system, where changes in one region propagate across the globe through atmospheric circulation, where the grinding of glaciers in Canada can contribute to soil formation in Nebraska, where the fertility of the Amazon depends on sand from the Sahara. In the microscopic particles that traveled on ancient winds lies a story of planetary connection, of how the solid Earth participates in its own constant reorganization, redistributing itself grain by grain according to the patient logic of wind and weather, and the eternal dance between erosion and deposition that shapes the surface of our living planet. The Ice Ages brought the twilight of mammoths, saber-toothed cats, and giant ground sloths. Was it the cold, or was it us? Their disappearance remains both tragedy and riddle, written in the fossil record like a mystery novel missing its final pages. There is something profoundly melancholic about the end of the Pleistocene megafauna, a sadness that goes beyond the simple fact of extinction to touch something deeper about the nature of loss itself. These were not just large animals, but entire worlds made flesh: the woolly mammoth with its curved tusks and shaggy coat, the saber-toothed cat with its impossible canine teeth, the giant ground sloth that could rear up on its hind legs to browse leaves 20 feet above the ground. They were the last representatives of evolutionary experiments that had been running for millions of years. And when they disappeared, they took with them ways of being alive that had never existed before and would never exist again. The timing of these extinctions is what makes them so haunting. For most of the Pleistocene epoch, the Ice Age megafauna had survived glaciation after glaciation, adapting to the rhythm of advancing and retreating ice sheets that had defined their world for more than 2 million years. The woolly mammoth had weathered dozens of climate cycles, migrating north and south with the ice, finding refuge in the grasslands that appeared and disappeared as sea levels fell and rose. The cave bear had survived winter after winter in the deep caves of Europe, emerging each spring to find a world that might be warmer or colder than the one they had left behind, but that still contained the resources they needed to survive. Yet, as the last ice age ended and the world began its transition into the warm Holocene period that would nurture human civilization, something went wrong. within the span of a few millennian eye blink in evolutionary time. Most of the large-bodied species that had dominated Ice Age ecosystems simply vanished. In North America, 35 genera of large mammals disappeared, including mammoths, mastodons, giant beavers, short-faced bears, and American cheetahs. In Australia, the extinction was even more dramatic, claiming not just the giant marsupials, but also massive reptiles like the monitor lizard Megalania, which could grow to 25 feet in length. The mystery deepens when we examine the pattern. Of these extinctions, small mammals largely survived the transition from glacial to interglacial conditions, as did most birds, reptiles, and marine species. The extinctions were heavily biased toward large-bodied animals, particularly those weighing more than 100 pounds. This size selectivity suggests that whatever caused the extinctions specifically targeted the ecological niches occupied by large herbivores and the carnivores that depended on them, while leaving smaller species largely untouched. Climate change alone cannot explain this pattern. The warming that marked the end of the last ice age was dramatic, but not unprecedented. Similar transitions had occurred dozens of times during the Pleistocene without triggering mass extinctions of megafauna. In fact, some of the extinct species had survived previous interglacial periods that were even warmer than the Holocene. The mammoth steppe ecosystem that supported vast herds of large grazers had contracted and expanded with each glacial cycle, but had always recovered when conditions became suitable again. This is where humans enter the story, and where the mystery becomes more complex and troubling. The end Pleistocene extinctions coincided remarkably closely with the spread of modern humans into previously uninhabited continents. In Australia, the megafaunal extinctions occurred around 50,000 years ago, shortly after the first human arrival. In the Americas, most of the extinctions happened between 13 and 10,000 years ago, overlapping with the period when human populations were expanding rapidly across both continents following their arrival via the Bering Land Bridge. The correlation is striking, but correlation is not causation, and the mechanisms by which relatively small human populations could have driven dozens of large mammal species to extinction remain hotly debated. The overkill hypothesis suggests that Ice Age humans, equipped with sophisticated hunting technologies and entering plus ecosystems filled with animals that had no evolutionary experience with human predation, could have hunted the megafauna to extinction within a few centuries. Computer models show that even modest hunting pressure by growing human populations could have pushed large, slow-reproducing species beyond their capacity to maintain stable populations. But the evidence for this direct hunting scenario is surprisingly sparse, and many of them show signs of scavenging rather than active hunting. The Clovis culture of North America, long thought to be responsible for the American megafaunal extinctions, shows evidence of hunting mammoths and mastodons. But these kill sites represent only a tiny fraction of the millions of individual animals that would have had to be killed to drive entire species to extinction. Perhaps the relationship between humans and megafaunal extinction was more subtle and indirect. Human activities may have disrupted Ice Age ecosystems in ways that made them unsuitable for large herbivores without necessarily involving direct predation. The use of fire to manage landscapes, for instance, could have altered vegetation patterns, and eliminated the grasslands that supported mammoth and bison populations. Competition for resources during the stressed conditions of deglaciation might have pushed large mammal populations below sustainable levels, even without active hunting. Disease represents another possible mechanism, though one that is even more difficult to trace in the archaeological record. Humans arriving in new continents would have brought with them pathogens from their regions of origin, and they may also have brought domestic dogs whose diseases could have jumped to wild carnivore populations. The megafauna of Australia and the Americas, having evolved in isolation from Old World disease organisms, would have had no immunity to introduced pathogens. A single epidemic could have swept through entire populations of large mammals, leaving no trace in the fossil record except the sudden absence of species that had been abundant for millions of years. The extinction of ice age megafauna also represents a cascade of ecological consequences that extended far beyond the lost species themselves. Large herbivores are ecosystem engineers, animals whose activities modify their physical environment in ways that affect entire communities of other species. Mammoths and other Ice Age megaherbivores helped maintain the grassland ecosystems that dominated much of the northern hemisphere during glacial periods, preventing the encroachment of forests through their feeding and trampling activities. When these animals disappeared, the grasslands they had maintained began to give way to forests and tundra, fundamentally altering the structure of northern ecosystems. The disappearance of large carnivores had equally dramatic effects. Saber cats, short-faced bears, and dire wolves were apex predators that shaped the behavior and evolution of their prey species through millions of years of predator-prey interactions. When these predators vanished, the ecological relationships that had structured Ice Age communities for millennia suddenly collapsed, leaving behind ecosystems that were simpler, less diverse, and fundamentally different from anything that had existed during the Pleistocene. Perhaps most poignantly, the extinction of Ice Age megafauna represents the loss of evolutionary potential that had been accumulating for millions of years. Each extinct species carried within its genome solutions to biological problems that had been refined through countless generations of natural selection. The mammoth's adaptations to cold, the ground sloth's unique digestive system, the cave bear's hibernation physiology. Of this evolutionary information vanished forever when the last individuals of each species died. Now, as we face what many scientists call the sixth mass extinction, the loss of Ice Age megafauna takes on new relevance and urgency. The pattern of human-associated extinctions that began at the Pleistocene has continued and accelerated through the Holocene, claiming species on every continent and in every major ecosystem. The questions raised by the Ice Age extinctions, how human activities interact with environmental change to drive species loss, how quickly stable ecosystems can collapse when key species are removed, how much biological diversity can be lost before ecosystem function breaks down entirely, are the same questions we face today as we try to understand and prevent ongoing biodiversity loss. The ghosts of the Ice Age giants remind us that extinction is forever, that the evolutionary experiments represented by vanished species can never be repeated, and that the responsibility for preventing further losses rests with the same species that may have triggered the first wave of human-caused extinctions more than 10,000 years ago. In their silence lies both warning and challenge, the warning that even the most successful evolutionary strategies can be undone by rapid environmental change, and the challenge to use our unique capacity for foresight and planning to ensure that the current wave of extinctions does not complete the tragic work that began when the last mammoth fell in the snow and the Ice Age world passed forever into memory. Humans endured the cold, inventing fire, shelter, and memory itself. The Ice Ages shaped our species into survivors, carrying tools and myths carved from frost and fear, transforming us from another African primate into something unprecedented. In Earth's long experiment with consciousness, we are children of the ice in ways that go deeper than metaphor, deeper even than the genetic traces that modern science can read in our DNA. The long millennia when glaciers advanced and retreated across the northern continents were the crucible in which our species learned not just to survive, but to transcend the biological limitations that had constrained every other creature that walked the earth. In the face of cold that could kill, darkness that could drive madness, and scarcity that demanded impossible choices, we became something: noodle makers, storytellers, keepers of fire and memory. The archaeological record tells this story in fragments scattered across cave floors and buried in ancient campsites. But what it reveals is a transformation so profound that it amounts to a second Genesis. The humans who entered the Ice Ages were clever primates. They lived where the climate permitted, ate what the environment provided, and died when conditions became too harsh for their bodies to endure. The humans who emerged from the Ice Ages had learned to carry their own climate with them in the form of clothing and shelter, to extend the reach of their hands with tools, to preserve and share knowledge through language and ritual in ways that allowed each generation to build upon the discoveries of those who came before. Fire was perhaps the first and most fundamental of these Ice Age innovations, though calling it an innovation understates its revolutionary impact. Fire was stolen time, borrowed from the sun, and concentrated into something that could push back the cold and darkness that defined Ice Age existence. Around fires built in caves and shelters across Europe and Asia, human communities developed the social structures and cultural practices that would become the foundation of all subsequent civilizations. Fire extended the day, creating hours of light and warmth during which tools could be crafted, stories told, knowledge shared across generations. Fire made certain foods digestible and safe, expanding the range of resources that could sustain human populations. Fire was protection against the predators that hunted in the Ice Age darkness, a barrier of light and heat that transformed humans from prey into something that even the largest carnivores learned to respect. But fire required more than just the knowledge of how to create and maintain it. It required a complete reorganization of human social life around the demands of keeping flames alive through Arctic winters that could last for 8 months of the year. Someone had to gather fuel, tend the flames through the night, preserve coals through travel from one camp to another. Fire created the first human technology that was truly communal, requiring cooperation and shared responsibility in ways that no other tool demanded. Around those Ice Age hearths, humans learned to depend on each other in new ways, developing bonds of mutual obligation and shared culture that extended far beyond the immediate family groups that had characterized earlier human societies. Clothing represents another revolutionary adaptation, though one that has left almost no direct trace in the archaeological record. Organic materials preserve poorly over tens of thousands of years, but we can infer from the environments that Ice-aged humans successfully colonized that they had developed sophisticated techniques for creating insulation from animal hides and furs. The invention of sewn clothing was as significant as the domestication of fire, allowing humans to carry warm microclimates with them as they expanded into territories that would have been instantly fatal to naked primates. Clothing was wearable architecture, the first human technology that modified the body's relationship with its environment in ways that permitted survival in conditions far beyond the range of our biological adaptations. Shelter construction during the Ice Ages went far beyond the simple windbreaks and temporary lean-tos that characterize the architecture of most hunter-gatherer societies. In the Ukrainian steppes, archaeologists have found the remains of structures built from mammoth bones and tusks, requiring careful planning and considerable engineering skill to construct. These were not temporary camps, but substantial dwellings, designed to last through entire winters, complete with storage areas for food and fuel, sleeping platforms, and central hearths surrounded by carefully arranged seating areas. The construction of such shelters required not just technical knowledge, but also social organization, sophisticated enough to coordinate the efforts of dozens of individuals over extended periods of time. The tools that Ice Age humans developed reflect a level of technological sophistication that rivals anything produced by human societies until the development of metallurgy thousands of years later. Clovis spear points from North America represent a pinnacle of stone tool technology, with flaking patterns so precise and symmetrical that they approach the level of art. The atlatl, or spear thrower, multiplied the force that human arms could generate, allowing hunters to bring down animals as large as mammoths with projectiles launched from safe distances. Bone needles and awls, fishhooks and harpoon points, scrapers and cutting tools of dozens of different specialized designs. The Ice Age toolkit represents solutions to survival challenges that could only have been developed through generations of accumulated experience and deliberate innovation. But perhaps the most remarkable Ice Age innovation was language itself, or at least language as we understand it today. Complex, symbolic communication capable of transmitting abstract concepts, future plans, and accumulated cultural knowledge from one generation to the next. While the origins of human language remain hotly debated, the archaeological evidence suggests that the kind of sophisticated cultural transmission necessary to survive Ice Age conditions would have been impossible without linguistic capabilities approaching those of modern humans. The construction of complex tools, the maintenance of fire through long winters, the planning required for seasonal migrations, all of these activities require the ability to share detailed information about techniques, timing, and environmental conditions in ways that go far beyond simple gesture and demonstration. Ice Age art provides some of the clearest evidence for the emergence of modern human consciousness. The cave paintings of Lascaux and Altamira, the carved figurines found in sites across Europe, the complex symbolic markings that appear on tools and ornaments, all of this represents a fundamental shift in human cognition, the development of minds capable not just of solving immediate practical problems, but of creating meaning, beauty, and symbolic representation. These are the minds that learned to see patterns in the movements of herds and the changing of seasons, to predict the behavior of prey animals and the arrival of storms, to imagine futures different from the present, and to plan accordingly. The genetic legacy of Ice Age survival is written in our DNA, but it extends beyond simple adaptation to cold environments. Modern humans carry genetic variants that were selected for during the Ice Age's alleles that improve cold tolerance, enhance fat metabolism, increase resistance to certain diseases, and even influence cognitive traits like spatial reasoning and long-term planning ability. We are, quite literally, evolved Ice Age survivors, shaped by tens of thousands of years of selection pressure for the physical and mental traits that allowed our ancestors to endure conditions that eliminated most other large mammal species. But the Ice Ages shaped more than our biology. They shaped our psychology, our social structures, our fundamental relationship with the natural world. The experience of living through long winters when a single mistake in planning or execution could mean death for an entire family group created selection pressure for traits like risk assessment, delayed gratification, and cooperative problem solving that continue to characterize human behavior today. The need to maintain complex toolkits and cultural knowledge through purely oral transmission favored individuals with exceptional memory abilities and strong social bonds. The requirement for flexible responses to unpredictable environmental changes selected for cognitive traits like creativity, abstract reasoning, and the ability to learn rapidly from experience. Perhaps most profoundly, the Ice Ages taught our species the power and necessity of cultural evolution as a complement to biological evolution. While other species adapted to Ice Age conditions through genetic changes that required thousands of generations, humans learned to adapt through cultural innovation that could spread through entire populations within a single generation. The invention of new tools, new survival techniques, new forms of social organization could be shared, modified, and improved upon in ways that allowed human populations to track environmental changes much more rapidly than would have been possible. Through genetic adaptation alone, this cultural capacity for rapid adaptation became the foundation for everything that followed in human history. The agricultural revolution, the development of cities and states, the scientific and industrial revolutions, all of these represent extensions of the same cultural learning mechanisms that first emerged as adaptations to Ice Age survival challenges. We learned to be human during the Ice Ages, and in doing so we became the first species in Earth's history capable of deliberately directing our own evolution and that of the ecosystems around us. The human shadow that falls across the late Pleistocene landscape is thus both literal and metaphorical, the actual presence of our species in environments where we had never existed before, but also the beginning of our emergence as a geological force capable of reshaping the planet itself. The Ice Ages ended not just with climate change, but with the appearance of a new kind of creature, one that would prove capable of triggering its own ice ages, warming its own climate, and ultimately determining the fate of most other species. On Earth, we emerged from the ice, carrying fire and tools and stories. But we also emerged, carrying a responsibility that no species had ever borne before, the responsibility that comes with the power to shape the world according to our own desires and the wisdom to understand the consequences of that power. Where there is ice, there is fire. Volcanic eruptions pierced glacial skies, leaving ash in ice cores like punctuation marks in history. Fire and ice are twin forces shaping Earth, locked in an eternal dance of creation and destruction that writes the planet's autobiography in stone and flame. The relationship between fire and ice during the glacial epochs was more intimate and complex than simple opposition. While vast ice sheets pressed down on the northern continents, the Earth's molten interior continued its restless churning, pushing magma toward the surface through volcanic vents that pierced even the thickest accumulations of ice. The weight of glaciers themselves sometimes triggered volcanic activity, as the massive load of ice compressed and then suddenly released the underlying crust, creating fractures through which lava could flow and ash could explode toward the sky. In Iceland, this marriage of fire and ice continues today, offering a window into the volcanic landscapes that must have characterized many glaciated regions during the Pleistocene. Beneath the Vatnajökull ice cap, subglacial volcanoes create a hidden world of fire and steam. Their eruptions melting vast chambers in the overlying ice and sending sudden floods of meltwater rushing across the landscape. When these eruptions break through to the surface, they create spectacular displays of lava fountains and ash plumes rising through curtains of falling snow. The ultimate expression of elemental forces meeting in violent embrace, the volcanic record preserved in ice. Cores tell stories of fire that shaped Ice Age climates in ways both subtle and dramatic. Major volcanic eruptions inject enormous quantities of ash and sulfur compounds into the stratosphere, where they can remain suspended for years, reflecting sunlight back to space and cooling global temperatures. During ice ages, when the climate system was already balanced on the edge between warming and cooling, these volcanic winters could tip entire regions into deeper glaciation or delay the retreat of ice sheets that might otherwise have begun to melt. The Toba supervolcanic eruption, which occurred in Sumatra approximately 74,000 years ago during the last glacial period, represents perhaps the most dramatic example of fire influencing ice in Earth's recent history. This colossal eruption ejected more than 2,800 cubic kilometers of material into the atmosphere, creating a volcanic winter that may have lasted for years and reduced global temperatures by several degrees. Some scientists hypothesize that this event pushed human populations to the brink of extinction, creating a genetic bottleneck that can still be detected in modern human DNA. Whether or not the Toba eruption came close to ending our species' story, it certainly demonstrates the power of volcanic fire to influence Ice Age climates and the course of evolution itself. But volcanic activity during ice ages was not merely destructive, it was also profoundly creative, building new landscapes and creating opportunities for life to persist in otherwise hostile environments. Volcanic heat sources provided refugia, where plants and animals could survive even during the coldest phases of glaciation, creating islands of warmth in an otherwise frozen world. Hot springs, heated by geothermal activity, remained liquid throughout the longest winters, providing water sources for Ice Age wildlife and early human populations. Volcanic soils, enriched with minerals from deep within the earth, supported vegetation that could feed herbivore populations during the brief summer growing seasons. The interplay between volcanic fire and glacial ice also created some of the most spectacular geological formations on Earth. When lava flows encounter ice sheets, the rapid cooling creates distinctive rock formations with characteristic shapes and textures. Pillow lavas form when molten rock flows into water or wet sediments, creating bulbous, pillow-like structures that preserve the exact moment when fire met ice. Table mountains and ridges mark the locations where volcanic eruptions occurred beneath ice sheets, their flat tops marking the level of the overlying glacier that contained and shaped the rising lava. Fire, in the form of human-controlled combustion, also played a crucial role in Ice Age ecosystems, though on a much smaller scale than volcanic activity. The ability to create and maintain fire allowed human populations to survive in environments that would otherwise have been uninhabitable. But it also gave them the power to modify those environments in subtle but significant ways. Archaeological evidence suggests that Ice-aged humans used fire not just for warmth and cooking, but also as a tool for landscape management, burning grasslands to improve grazing for the animals they hunted, and clearing forests to create more open environments. These human fires, small as they were compared to natural wildfires or volcanic eruptions, may have had disproportionate ecological effects during ice ages when ecosystems were already stressed by cold and aridity. The use of fire to drive game animals toward hunters or to clear migration routes may have contributed to the extinction of Ice Age megafauna by disrupting traditional patterns of movement and feeding. The burning of vegetation to create more favorable hunting conditions may have altered the composition of plant communities in ways that persisted long after the fires themselves had burned out. The ash layers preserved in ice cores also document natural wildfires that swept across Ice Age landscapes, often triggered by lightning strikes, but sometimes burning for months or years in the organic soils of northern peatlands. These fires were part of the natural cycle of many Ice Age ecosystems, clearing accumulated plant material and returning nutrients to the soil while creating the open, grassy conditions that supported large herbivore populations. The frequency and intensity of these natural fires varied with climate conditions, increasing during dry periods and decreasing when cooler, wetter conditions prevailed. Volcanic fire also influenced Ice Age climates through more subtle mechanisms than dramatic eruptions and ash clouds. The gradual outgassing of carbon dioxide from volcanic sources helped maintain atmospheric greenhouse gas concentrations during glacial periods when biological processes were removing carbon dioxide from the air through reduced plant growth and altered ocean chemistry. Without this volcanic input of greenhouse gases, ice ages might have been even more severe and long-lasting than they actually were, potentially creating runaway cooling that could have turned Earth into a permanently frozen snowball planet. The relationship between fire and ice during glacial periods also extended into the realm of chemistry and atmospheric composition. Volcanic emissions of sulfur compounds created acid rain that altered the pH of lakes and rivers across vast regions, affecting aquatic ecosystems and the terrestrial food webs that depended on them. The interaction between volcanic gases and ice age atmospheric conditions created complex chemical reactions that influenced ozone levels, atmospheric moisture, and the formation of clouds in ways that fed back into the climate system. Perhaps most remarkably, the marriage of fire and ice during glacial periods created conditions that may have been crucial for the preservation of life through the most severe cooling events. Volcanic heat sources provided thermal refugia where species could survive periods of extreme cold, while the minerals released by volcanic activity enriched soils and water sources in ways that supported biological productivity even during the harshest phases of glaciation. The hot springs and geothermal areas that dot volcanic landscapes today are modern analogues of the warm oases that must have sustained life throughout the ice ages. The legacy of Ice Age fire persists in landscapes around the world, written in the volcanic rocks that formed beneath ancient glaciers and the ash layers that mark specific eruptions in the geological record. The Yellowstone region, with its combination of geothermal features and evidence of past glaciation, provides a glimpse of what vast areas of North America and Europe must have looked like during the Pleistocene, a world where fire and ice coexisted in intimate relationship, each shaping the other through complex feedback mechanisms that operated across multiple time scales. As we contemplate the possibility of future climate changes, the Ice Age record of fire and ice interactions offers both insights and warnings. It reminds us that the Earth's climate system includes many variables beyond simple temperature and precipitation, that volcanic activity can influence regional and global climates in ways that are difficult to predict, and that the interplay between different Earth system components can create surprises that challenge our understanding of how the planet works. The dance between fire and ice that characterized the Pleistocene continues today, though in different forms and at different scales, as humanity learns to harness both volcanic energy and glacial ice as sources of power, while grappling with our own role as a geological force capable of influencing both. Beneath Antarctic and Greenland sheets lie hidden lakes, sealed off for millions of years. What unknown life whispers in these dark waters, untouched by the sun? And what secrets do they hold about the persistence of life in Earth's most extreme environments? There is something profoundly mysterious about water that has been locked away from the surface world for longer than complex life has existed on Earth. Deep beneath the Antarctic ice sheet, in lakes that have been isolated from the atmosphere for millions of years, water flows in eternal darkness, warmed by geothermal heat from the planet's interior and sealed from above by ice that may be several miles thick. These are not small ponds, but vast bodies of water. Lake Vostok, the largest known subglacial lake, covers an area larger than Lake Ontario and contains water that has been cut off from the surface for at least 15 million years. The very existence of liquid water beneath ice sheets that are themselves manifestations of extreme cold speaks to the complex physics that governs the behavior of ice under pressure. The immense weight of glacial ice creates pressure that lowers the melting point of water, while geothermal heat from the Earth's interior provides enough energy to maintain liquid conditions at the interface between ice and bedrock. The result is a hidden hydrological system of rivers, lakes, and streams flowing beneath some of the most seemingly desolate landscapes on Earth, creating aquatic environments that may be among the most isolated and pristine ecosystems on the planet. Scientists have identified more than 400 subglacial lakes beneath the Antarctic ice sheet, connected by a network of subglacial rivers that flow according to the topography of the underlying bedrock rather than the surface features visible from above. These hidden waterways carry sediments, nutrients, and potentially living organisms across hundreds of miles of subglacial terrain, creating opportunities for biological exchange and colonization that would be impossible in the frozen world above. Some of these subglacial rivers are substantial enough to influence the flow of the overlying ice sheet, lubricating its movement and affecting the rate at which glaciers slide toward the sea. The question of life in these subglacial environments has fascinated scientists since the lakes were first discovered through ice penetrating radar in the 1970s. These are environments that challenge every assumption about the limits of biological possibility: permanently dark, extremely cold, under crushing pressure, and isolated from the surface sources of organic matter that fuel most ecosystems. Yet they are also remarkably stable environments, with temperatures that remain constant for millions of years and chemical conditions that may be ideal for certain types of microorganisms. The first direct evidence of life in subglacial lakes came from ice cores drilled just above Lake Vostok, where scientists found bacterial DNA frozen in ice that had formed at the lake's surface and then been incorporated into the overlying ice sheet. These genetic signatures suggested the presence of diverse microbial communities adapted to the extreme conditions of subglacial life, including bacteria that derive energy from chemical reactions rather than photosynthesis, and archaea that thrive in conditions that would be toxic to most surface-swelling organisms. More recent drilling projects have begun to directly sample the water and sediments of subglacial lakes, revealing ecosystems that are both alien and familiar. The microorganisms found in these environments include species that are closely related to bacteria found in other extreme environments around the world: hot springs, deep ocean vents, highly saline lakes, suggesting that life has found ways to persist in the subglacial realm using many of the same biochemical strategies that allow organisms to survive in other challenging habitats. But subglacial lakes are not simply repositories of extremophile bacteria. The sediments that accumulate on their floors contain records of environmental conditions that extend back millions of years, preserving information about past climate changes, ice sheet dynamics, and potentially even the evolution of life in these isolated environments. Some of these sediment records may extend back to periods when Antarctica was much warmer than it is today, when forests covered regions that are now buried beneath miles of ice, when the ancestors of modern subglacial organisms first colonized the spaces beneath the growing ice sheet. The chemistry of subglacial lake waters provides clues about the processes that sustain life in these environments. Many subglacial lakes are highly enriched in dissolved minerals, particularly iron, sulfur, and other elements that can support chemosynthetic metabolism, the process by which organisms derive energy from chemical reactions rather than sunlight. The water in these lakes is often supersaturated with gases like methane and hydrogen, creating chemical conditions that may be similar to those that existed in Earth's early oceans when life first evolved. The isolation of subglacial lakes also makes them natural laboratories for studying evolution in closed systems. Organisms trapped in these environments for millions of years would have evolved independently from their surface relatives, potentially developing unique adaptations to subglacial conditions. Some scientists speculate that subglacial lakes might contain living fossils organisms that preserve characteristics of ancient life forms that have long since gone extinct in surface environments. Others suggest that the extreme conditions might have driven unusually rapid evolution, producing highly specialized organisms. Unlike anything found elsewhere on Earth, the discovery of subglacial lakes has also revolutionized our understanding of ice sheet dynamics and their role in global climate systems. The lubrication provided by subglacial water can dramatically affect the rate at which ice sheets flow toward the ocean, influencing sea level rise and the stability of ice sheets. In response to climate change, the heat generated by geothermal activity beneath ice sheets can create zones of rapid melting that are invisible from the surface, but that may play crucial roles in determining how ice sheets respond to warming temperatures. As climate change accelerates the melting of ice sheets around the world, the fate of subglacial ecosystems becomes increasingly uncertain. Some subglacial lakes may be exposed to the surface for the first time in millions of years as overlying ice melts away, while others may experience changes in water chemistry, temperature, and conductivity as the hydrological systems that sustain them are altered by changing ice dynamics. These changes could provide unprecedented opportunities to study subglacial life, but they could also threaten ecosystems that have persisted unchanged for geological timescales. The study of subglacial lakes also has implications for astrobiology and the search for life on other planets. The conditions beneath Earth's ice sheets may be similar to those that exist beneath the ice-covered surfaces of moons like Europa and Enceladus, making subglacial lakes natural analogs for extraterrestrial environments where life might exist. The organisms found in these hidden waters demonstrate that life can persist in environments that seem utterly hostile to biological activity, expanding our conception of where life might be found in the universe and what forms it might take. Perhaps most remarkably, subglacial lakes remind us that Earth still holds secrets, that there are entire ecosystems on our planet that remain largely unexplored and poorly understood. These hidden seas beneath the ice represent frontier environments as alien as any extraterrestrial landscape, places where life has learned to persist in conditions that challenge our basic assumptions about biological possibility. They are windows into alternative ways of being alive, laboratories where evolution has conducted experiments in isolation for millions of years, and repositories of environmental information that could transform our understanding of how Earth's climate system has operated throughout deep time. In their dark waters lies both mystery and revelation, the mystery of how life adapts to conditions that seem impossible, and the revelation that even in Earth's most extreme environments, life finds a way to persist, to evolve, to create ecosystems of remarkable complexity and beauty. The sea beneath the ice whispers stories of persistence and adaptation that stretch back millions of years, reminding us that life is more resilient, more creative, and more widespread than we have ever imagined. Glaciers are memory made solid. Each layer is a page, and together they form Earth's oldest library. But as they melt, those books vanish unread, taking with them the accumulated wisdom of hundreds of thousands of years of climate history. There is something both heartbreaking and profound about the way ice remembers. Unlike human memory, which fades and shifts and reconstructs itself with each recollection, glacial memory is precise and permanent, locked into crystal structure and chemical composition with an accuracy that would shame any historian. Each snowflake that falls and compresses into ice carries within it the exact atmospheric conditions of the moment it formed: the temperature, the humidity, the concentration of gases, even the microscopic particles of dust and volcanic ash that were suspended in the air when that water first crystallized into its hexagonal architecture. The great ice sheets of Greenland and Antarctica are archives that dwarf any human library, containing detailed records of atmospheric composition, temperature, and precipitation patterns stretching back nearly 1,000,000 years. The ice core, extracted from the deepest drilling sites, read like chronicles, written in a language of isotopes and trace gases, each annual layer marking another year in the Earth's long autobiography. Scientists can determine not just the average temperature of ancient years, but the season-by-season variations, the timing of storms, the frequency of volcanic eruptions, the changing patterns of ocean circulation and atmospheric chemistry that shaped the climate of the distant past. But glacial memory extends far beyond the chemical signals preserved in ice cores. The physical structure of glaciers themselves records the mechanical history of their formation, the patterns of accumulation and flow that shaped them over centuries or millennia. The layers visible in exposed glacier faces tell stories of heavy snow years and drought years, of periods when the ice flowed rapidly and times when it nearly stopped, of sudden changes in climate that are written in the ice as clearly as if they had been carved there by human hands. Moraines, the ridges of rock and sediment, bulldozed along by advancing glaciers, preserve the memory of ice sheet movements with surveyor-like precision. Each moraine marks a position where a glacier front remained stable for decades or centuries, accumulating debris in linear ridges that can be traced across entire continents. The terminal moraines, left by the great ice sheets of the last glaciation, stretch from Long Island to the Pacific Northwest, marking the maximum extent of ice advance with a clarity that allows modern scientists to reconstruct ice sheet boundaries with remarkable accuracy. Erratic boulders scattered across landscapes, hundreds of miles from their points of origin, carry the memory of glacial transport in their very displacement. These rocks, some as large as houses, were plucked from distant bedrock exposures and carried by ice sheets across entire regions before being deposited when the ice finally melted. Each erratic is a witness to the immense power and reach of Glacial transport, a piece of geological evidence that speaks of ice sheets capable of moving mountains, grain by grain, across vast distances. The memory preserved in glaciers is not limited to physical and chemical records. It also includes biological information of extraordinary richness and diversity. Ancient DNA extracted from ice cores has revealed the presence of bacteria, plants, and even larger organisms that lived in glacial environments hundreds of thousands of years ago. This genetic material provides direct evidence of how life adapted to Ice Age conditions and how ecosystems responded to rapid climate changes in the past. Pollen grains and other organic materials trapped in ice offer insights into the vegetation patterns and atmospheric conditions that existed when the ice formed. Perhaps most remarkably, some of this biological material is still viable after hundreds of thousands of years of preservation in ice. Scientists have successfully cultured bacteria that had been frozen in glacial ice for more than 750,000 years, demonstrating that ice can preserve not just the memory of life, but life itself. These ancient organisms, awakened from their frozen sleep, provide living links to ecosystems that disappeared long before human civilization began, offering unprecedented opportunities to study how life responds to extreme environmental conditions. The precision of glacial memory is almost incomprehensible when measured against human timescales. Ice cores can resolve environmental changes that occurred within individual years, sometimes even individual seasons, providing a temporal resolution that approaches that of written historical records, but extending back hundreds of times further than any human documentation. The volcanic eruption that created the year without a summer in 1815. The dust storms of the 1930s Dust Bowl, the beginning of the Industrial Revolution. All of these recent events appear in ice core records as distinct chemical signatures that can be dated with extraordinary precision. But glacial memory is not evenly distributed across the planet. The ice sheets that preserve the longest and most detailed records are confined to the polar regions and high mountain areas, creating geographical biases in our understanding of past climate changes. The memory of ice is richest where ice is thickest and most stable, but these locations may not be representative of the climate conditions that affected most of Earth's surface or most of its living organisms. The challenge for scientists is to extract global climate signals from these localized ice sheet records and to integrate glacial memory with other forms of paleoclimatic evidence. Climate change is now threatening the very archives that have allowed us to understand how climate has changed in the past. As global temperatures rise, glaciers around the world are retreating and melting at accelerating rates, potentially destroying climate records that took hundreds of thousands of years to accumulate. Some mountain glaciers have already disappeared entirely, taking with them irreplaceable archives of regional climate history. Even the great ice sheets of Greenland and Antarctica are showing signs of accelerating mass loss that could compromise their value as climate archives within decades. The loss of glacial memory has implications that extend far beyond the scientific community. These ice archives contain information about how Earth's climate system responds to changes in atmospheric composition, how rapidly climate can shift from one state to another, and how different regions of the planet are connected through atmospheric and oceanic circulation patterns. This information is crucial for understanding and predicting how current climate changes might unfold, providing essential context for distinguishing natural climate variability from human-induced changes. Efforts to preserve glacial memory before it melts away have become increasingly urgent. Scientists are drilling ice cores from threatened glaciers around the world, racing against time to extract climate records before they are lost forever. These efforts require enormous logistical coordination and technical expertise, involving teams of researchers working in some of the most remote and challenging environments on Earth. The ice cores they recover are stored in specialized freezers that maintain temperatures cold enough to preserve the ice indefinitely, creating libraries of glacial memory that future scientists will be able to study long after the original glaciers have vanished. The preservation of glacial memory also raises profound questions about our responsibility to future generations. The climate records contained in glacial ice represent a form of natural heritage that is irreplaceable once lost, a scientific and cultural resource that has taken hundreds of thousands of years to accumulate. The decision to protect or exploit glaciated regions involves not just immediate economic considerations, but also the preservation of information that could be crucial for understanding and adapting to future climate changes. As we face the possibility that much of Earth's glacial memory may disappear within our lifetimes, we are confronted with the paradox that our own activities are destroying the very archives that could help us understand the long-term consequences of those activities. The memory of ice holds keys to understanding how Earth's climate system works, how it has responded to changes in the past, and how it might respond to the changes we are imposing on it today. In losing that memory, we lose not just scientific data, but a form of planetary consciousness, the accumulated wisdom of hundreds of thousands of years of Earth's experience with climate change. The memory of ice reminds us that the Earth itself is a conscious entity in ways that transcend metaphor, a planet that records and remembers its own history with a precision and longevity that puts human memory to shame. In the crystalline structure of glacial ice lies a form of planetary intelligence, a way of knowing and remembering that connects us to the deepest patterns of climate and atmosphere and ocean that have shaped our world since long before our species existed. As that memory melts away, we lose more than data. We lose a connection to the deep time perspective that could teach us how to live sustainably on a planet whose memory is longer and more accurate than our own. Milankovitch cycles, planetary tilts, and solar rhythms guided the ice ages. The cosmos itself is inscribed in the ice, binding us to the movement of stars and the orbital dance that governs the long seasons of our planet's climate history. There is something almost mystical about the realization that the ice ages were choreographed by celestial mechanics, that the advance and retreat of continental glaciers was governed by the same gravitational forces that keep planets in their orbits and moons circling around their parent worlds. The Earth's relationship with the Sun is not constant, but oscillates in regular patterns that stretch across tens of thousands of years, creating cycles of warming and cooling that operate with the precision of an astronomical clock built from Orbital Mechanics and Planetary Physics. Milutin Milankovitch, the Serbian mathematician who first calculated these astronomical cycles in the early 20th century, was attempting to solve one of the great puzzles of his time. What caused the ice ages? The geological evidence for repeated glaciation was overwhelming, but the mechanisms that could drive such massive climate changes remained mysterious. By applying celestial mechanics to the problem of climate change, Milankovitch revealed that the Earth's orbit around the Sun and the orientation of its rotational axis change in predictable ways that alter the distribution of solar energy across the planet's surface. The first and most fundamental of these cycles involves changes in the shape of Earth's orbit around the Sun. Like all planetary orbits, Earth's path around the Sun is not a perfect circle, but an ellipse that changes shape over time. This orbital eccentricity varies on a cycle of approximately 100,000 years, alternately bringing Earth slightly closer to or farther from the Sun during specific seasons. When the orbit is more eccentric, the difference between the closest and farthest approaches to the Sun is more pronounced, creating greater seasonal variations in the amount of solar energy reaching Earth. The second cycle involves changes in the tilt of Earth's rotational axis, known as obliquity. Currently, Earth's axis is tilted at approximately 23.5 degrees relative to its orbital plane, creating the seasonal variations in day length and solar intensity that drive our annual climate cycle. But this tilt is not constant. It oscillates between 22.1 and 24.5 degrees over a period of about 41,000 years. When the tilt is greater, seasonal variations are more extreme, with hotter summers and colder winters. When the tilt is smaller, seasons are more moderate, potentially allowing winter snow to persist through milder summers in polar regions. The third cycle involves the precession of Earth's rotational axis, a slow wobble similar to the motion of a spinning top as it slows down. This precession has a period of approximately 26,000 years and determines which season occurs when Earth is closest to the Sun. Currently, Earth reaches its closest approach to the Sun during Northern Hemisphere winter, slightly moderating winter temperatures in the north while intensifying them in the south. But 13,000 years ago, the closest approach occurred during northern summer, creating more intense seasons in the Northern Hemisphere. When Milankovitch first proposed these astronomical explanations for ice ages, the geological evidence seemed to support cycles of approximately 100,000 years, matching the eccentricity cycle but not obviously correlating with the shorter obliquity and precession cycles. This created what came to be known as the 100,000-year problem. Why should the weakest of the three astronomical cycles dominate the Ice Age record? The resolution of this puzzle required a deeper understanding of how Earth's climate system responds to orbital forcing through complex feedback mechanisms that can amplify small astronomical signals into major climate changes. The key insight came from recognizing that ice sheet growth and decay involve powerful positive feedback loops that can transform gradual astronomical forcing into rapid climate transitions. When orbital cycles reduce summer solar radiation in the northern hemisphere, snow that accumulates during winter may persist through the following summer, beginning the process of ice sheet formation. Once established, ice sheets create their own feedback loops. Their white surfaces reflect solar radiation back to space. cooling regional temperatures and promoting further ice accumulation. The growing ice sheets also alter atmospheric circulation patterns and ocean currents in ways that can spread cooling effects far beyond the directly glaciated regions. Marine sediment core and ice core records have provided detailed confirmation of Milankovitch's theory, while also revealing the complex ways that astronomical cycles interact with Earth's climate system. The isotope records contained in these archives show clear signatures of all three astronomical cycles, but they also reveal that the climate system's response to orbital forcing has changed over time. During the past million years, the 100,000-year eccentricity cycle has indeed dominated Ice Age timing. But earlier in Earth's history, the 41,000-year obliquity cycle was more prominent, suggesting that the sensitivity of ice sheets to orbital forcing depends on other factors, such as atmospheric composition and continental configuration. The astronomical theory of ice ages also helps explain some of the most puzzling features of glacial cycles, including the asymmetry between gradual ice sheet growth and rapid deglaciation. Ice sheets typically take tens of thousands of years to build up to their maximum extent, but can collapse and retreat within a few thousand years when orbital conditions favor warming. This asymmetry reflects the different physical processes involved in ice accumulation and ice loss. Building ice sheets requires the gradual accumulation of snow over thousands of winters, while melting them can be accomplished relatively quickly once temperatures rise above critical thresholds. The precision of astronomical cycles has allowed scientists to calculate past and future orbital configurations with remarkable accuracy, providing a cosmic calendar that extends millions of years into the past and future. Based on current orbital parameters, the next ice age should begin sometime within the next 50,000 to 80,000 years. As decreasing northern hemisphere summer, solar radiation allows ice sheets to begin growing in northern Canada and Scandinavia. However, human activities have complicated this astronomical forecast by altering atmospheric greenhouse gas concentrations in ways that could delay or prevent the next glaciation entirely. The relationship between astronomical cycles and ice ages also illustrates the deep connections between Earth's climate system and the broader cosmos. The gravitational influences of other planets, particularly Jupiter and Saturn, affect the shape of Earth's orbit and the orientation of its axis, making Ice Age timing dependent on the configuration of the entire solar system. Even more distant astronomical phenomena, such as the Sun's passage through different regions of the galaxy and variations in cosmic ray flux, may influence Earth's climate over longer timescales, connecting the history of glaciation to the motion of stars and the structure of the Milky Way itself. The discovery that ice ages are driven by astronomical cycles has profound implications for understanding Earth as a planet and our place within the solar system. It reveals that Earth's climate is not an isolated system, but is intimately connected to cosmic processes that operate on scales far larger than the terrestrial environment. The ice that accumulates in polar regions during glacial periods, responding to gravitational forces that originate in the orbital motions of planets and the nuclear fusion processes occurring in the Sun's core. This cosmic perspective on climate change also provides important context for current discussions about anthropogenic global warming. The astronomical cycles that drive ice ages operate on timescales of thousands to hundreds of thousands of years, while human-induced climate changes are occurring over decades to centuries. This difference in timescales means that human activities are now overwhelming the natural orbital cycles, creating climate changes that are much more rapid than anything in the astronomical record of ice ages. The cycles written in stars remind us that Earth participates in cosmic rhythms that dwarf human timescales, that our planet's climate history is inscribed in orbital mechanics and celestial geometry. The ice ages were not random events, but expressions of the deep order that governs planetary motion and stellar evolution. In understanding these astronomical connections, we gain not just scientific knowledge, but also a sense of our place in a universe where the smallest changes in orbital parameters can reshape continents, where the tilt of a planet's axis can determine the fate of species, and where the rhythm of ice and warmth that has shaped our world for millions of years is ultimately written in the movements of celestial bodies across the vast architecture of space and time. Frozen soil preserves not only ancient plants, but bacteria, viruses, and unknown DNA. In thaw, the shadows of deep time awaken, reminding us that nothing truly disappears, only sleeps, waiting for the right moment to return to the world of the living. Beneath the surface of northern Alaska, Siberia, and the Canadian Arctic lies a world suspended between life and death, a realm where time itself seems frozen, along with the organic matter that has accumulated there for hundreds of thousands of years. Permafrost, permanently frozen soil, more than just ice and earth. It is a vast repository of biological material that has been preserved in conditions so stable that DNA remains intact. Cells retain their structure, and entire organisms can be thawed back to life after millennia of suspended animation. The shadows on the permafrost are not metaphorical. They are literal remnants of worlds that existed when the Earth was different, when mammoths grazed on grasslands that stretched from Europe to Alaska, when forests grew where now only tundra survives, when the atmosphere itself had a different composition and different species breathed that ancient air. Every layer of permafrost is a time capsule, preserving not just individual organisms, but entire ecosystems in three-dimensional detail, complete with the bacteria in their guts, the pollen on their fur, the parasites in their blood. The preservation is so perfect that it challenges our understanding of the boundary between life and death. Scientists have successfully revived bacteria that had been frozen in permafrost for hundreds of thousands of years. Organisms that were alive when early humans were just beginning to use fire, when the continents were arranged differently, when species that are now extinct dominated the northern landscapes. These resurrected bacteria emerge from their frozen sleep with their metabolisms intact, their genetic information unchanged, their cellular machinery ready to resume the business of life as if no time had passed at all. But bacteria are not the only shadows lurking in the permafrost. Viruses, those strange entities that exist at the boundary between living and non-living matter, have also been found preserved in ancient ice and frozen soil. Some of these viruses are unlike anything in modern databases, representing lineages that diverged from contemporary forms millions of years ago. As permafrost melts due to climate change, these ancient pathogens are returning to environments where they have been absent for geological ages, potentially encountering host organisms that have no evolutionary history of exposure to them. The genetic material preserved in permafrost tells stories that go beyond individual organisms to encompass entire ecosystems and their responses to past climate changes. Environmental DNA genetic fragments shed by plants, animals, and microorganisms into soil and water accumulates in permafrost like pages in a book, creating archives of biological diversity that extend back far further than any other terrestrial record. Scientists can extract DNA from soil samples and identify the species that lived in particular locations at specific times in the past, reconstructing food webs and ecological relationships with a precision that would be impossible using traditional fossil methods. These molecular fossils reveal ecosystems that were more diverse and complex than we had previously imagined. The Mammoth Steppe, that vast grassland ecosystem that supported Ice Age megafauna, appears in permafrost DNA records as a biological community of extraordinary richness, with hundreds of plant species, diverse assemblages of small mammals, and intricate networks of predator-prey relationships. The genetic signatures of species that are now extinct appear alongside those of species that still exist, providing insights into how biological communities reassembled themselves as climate changed and ice sheets advanced and retreated. Perhaps most remarkably, some of the DNA preserved in permafrost belongs to organisms that were already ancient when the permafrost formed. Genetic material from bacteria and archaea that lived in earlier geological periods has been found preserved in sediments that were later frozen, creating archives within archives, nested time capsules that preserve biological information from multiple geological epochs. These discoveries suggest that permafrost regions may contain genetic libraries spanning millions of years of evolutionary history, libraries that are now being opened for the first time as warming temperatures cause widespread melting. The thawing of permafrost is not just releasing ancient biological material. As frozen soils melt, previously isolated microbial communities are coming into contact with each other and with modern organisms, creating possibilities for horizontal gene transfer, viral evolution, and the emergence of novel biological entities. The permafrost zones that are experiencing the most rapid warming are becoming natural laboratories for studying how ancient and modern life forms interact when they are suddenly brought together after millions of years of separation. The shadows preserved in permafrost also include the remains of human activities from much more recent periods. Archaeological sites in the Arctic have preserved organic materials with such fidelity that scientists can extract DNA from human hair, analyze the contents of ancient cooking pots, and identify the specific species of wood that were used to build structures thousands of years ago. These sites provide insights into how indigenous peoples adapted to changing climate conditions in the past and how their activities influenced northern ecosystems over long periods of time. Climate change is now exposing permafrost that has been frozen for hundreds of thousands of years, revealing biological treasures that have been locked away since before human civilization began. But this exposure is a double-edged phenomenon. While it provides unprecedented opportunities for scientific discovery, It also represents the irreversible loss of preservation conditions that took geological ages to establish. Once permafrost melts, the organic material it contains begins to decompose rapidly, releasing carbon dioxide and methane into the atmosphere, while destroying the biological archives that could have provided insights into Earth's climate and ecological history. The decomposition of permafrost organic matter is also creating positive feedback loops that accelerate climate change. As frozen soil melts, the organic matter it contains becomes available to soil microorganisms that break it down and release greenhouse gases. These emissions contribute to further warming, which causes more permafrost to melt, which releases more greenhouse gases in a self-reinforcing cycle that could significantly amplify human-induced climate change over the coming centuries. The microbial communities that become active as permafrost thaws are themselves products of ancient ecosystems, assemblages of bacteria and archaea that evolved under different climate conditions and may respond to modern warming in unpredictable ways. Some of these organisms may be adapted to metabolic processes that produce methane, a greenhouse gas that is much more potent than carbon dioxide. Others may be capable of breaking down organic compounds that have been stable for thousands of years, potentially releasing not just greenhouse gases, but also other compounds that could affect atmospheric chemistry and air quality. The shadows on the permafrost remind us that the Earth's system includes temporal dimensions that extend far beyond human experience, that the biological and chemical processes occurring today are influenced by events and organisms from the deep past. The permafrost regions of the world are not just landscapes, but time machines, preserving biological information from previous climate states and releasing it back into the modern world as warming temperatures reverse the freezing processes that created these vast natural archives. As we witness the awakening of these shadows from deep time, we are forced to confront the reality that our actions are not just changing the climate of the present, but also releasing the preserved remnants of ancient climates back into the contemporary world. The permafrost is melting not just ice and soil, but time itself, bringing the past into contact with the present in ways that blur the boundaries between geological history and human history, between ancient ecosystems and modern ones, between the shadows of what was and the uncertain light of what is yet to come. When glaciers collapse, they sing in low frequencies that vibrate like a heartbeat of the earth. Melting is not just silence, breaking it is the echo of time speeding up. The sound of geological processes compressed from millennia into moments. There is music in the death of glaciers, though it is not music that human ears were evolved to hear. Through solid earth and ocean water, with the deep, rumbling tones of a planet adjusting to sudden changes in its frozen burden. Seismologists have learned to listen to this music, using networks of sensitive instruments to detect the vibrations that mark the acceleration of ice loss and the reorganization of landscapes that have been stable for thousands of years. The sounds of melting ice span an enormous range of frequencies and amplitudes. At the smallest scale, the melting of individual ice crystals creates molecular vibrations too subtle to detect without sophisticated equipment. But these microscopic processes, multiplied across vast areas of ice sheets and glaciers, combine to create acoustic signatures that can be measured hundreds of miles away. The crackling of ice as it adjusts to changing temperatures, the groaning of glaciers as they accelerate their flow toward the sea, the thunderous crash of icebergs calving from ice sheet margins. All of these sounds carry information about the rates and mechanisms of ice loss. Scientists have discovered that glaciers and ice sheets are becoming more acoustically active as global temperatures rise. The frequency and amplitude of seismic signals generated by ice dynamics have increased dramatically in recent decades, particularly in regions like Greenland and West Antarctica, where ice loss is accelerating most rapidly. The Earth itself is becoming more musical, though it is a song of dissolution and change rather than stability and permanence. The acoustic signatures of ice sheet collapse are surprisingly diverse. Different types of ice loss generate different frequency patterns, allowing researchers to distinguish between gradual melting, rapid ice flow, iceberg calving, and sudden ice shelf collapse based on their seismic characteristics. The collapse of large ice shelves, like the Larsen B ice shelf in Antarctica, generates acoustic signals that can be detected around the world. The tempo of these ice songs is accelerating. Processes that once took centuries or millennia to unfold are now happening within decades or years. Glaciers that flowed at speeds measured in meters per year are now moving at rates of meters per day. Ice shelves that maintained their basic structure for thousands of years are disintegrating within seasons. The Earth's cryosphere is shifting from geological time to human time, from the slow rhythms of deep time to the rapid pulse of contemporary climate change. The echo of melting extends beyond simple acoustics to include the hydrological reverberations of ice loss. As glaciers and ice sheets melt, they release water that has been stored in solid form for hundreds or thousands of years, suddenly returning it to the active hydrological cycle. This pulse of meltwater affects ocean circulation, sea level rise, and regional precipitation patterns in ways that echo around the globe through interconnected Earth systems. The isotopic composition of glacial meltwater carries the chemical signature of the climate conditions under which the ice originally formed. Time periods as it mixes with contemporary ocean and atmospheric water. Water that fell as snow during the medieval warm period or the Little Ice Age is now returning to the oceans, carrying with it isotopic memories of past climate states. The biological echoes of ice melting are equally profound. As glaciers retreat, they expose landscapes that have been ice-covered for thousands of years, creating opportunities for biological colonization and ecosystem development in previously inaccessible areas. But they also disrupt established ecosystems by altering patterns of seasonal water availability, changing the timing and magnitude of river flows. By melting ice are not random noise, but carry specific information about the physical processes driving ice loss. The frequency content of seismic signals can reveal whether ice is melting from above due to warm air temperatures or from below due to warm ocean water. The spatial distribution of seismic sources can map the geographic patterns of ice. Networks now listen continuously to the sounds of the cryosphere, using arrays of seismometers, hydrophones, and other acoustic sensors to track ice dynamics in real time. These monitoring systems can detect ice sheet changes as they happen, rather than waiting for satellite measurements or field observations, providing early warning of rapid ice loss events and improving forecasts of sea level rise and other consequences of cryospheric change. The echo of melting also includes the atmospheric reverberations of ice loss. Large ice sheets create their own weather patterns through their effects on air temperature, humidity, and circulation. As these ice sheets shrink, they alter regional and even global atmospheric dynamics in ways that can affect weather patterns thousands of miles away. The loss of Arctic sea ice, for example, may be contributing to changes in mid-latitude weather patterns by altering the temperature gradient that drives atmospheric circulation. The psychological and cultural echoes of ice melting may be among the most profound of all. Indigenous communities in the Arctic have developed sophisticated knowledge systems based on intimate familiarity with ice conditions, seasonal patterns, and the behavioral signatures of different types of ice formation and melting. As rapid climate change alters these patterns faster than traditional knowledge can adapt. Entire ways of understanding and interacting with the environment are being disrupted. The sounds of melting ice also carry emotional resonances that connect human observers to the scale and urgency of environmental change in ways that abstract scientific data cannot match. The crack of calving icebergs, the rush of glacial streams, swollen with meltwater, the silence left behind when ancient ice finally disappears. These acoustic experiences create visceral connections to climate change that can motivate action and concern in ways that graphs and statistics cannot achieve. Perhaps most poignantly, the echo of melting represents the acceleration of geological time into human time. The compression of processes that normally unfold over millennia into changes that can be witnessed within individual lifetimes. The sounds we are now hearing from the world's ice sheets and glaciers are the acoustic signature of deep time colliding with present time, of ancient ice releasing its stored memories of past climates into a world that is changing faster than ice can adapt. The echo of melting is thus both literal and metaphorical, the actual acoustic signals. It is the sound of the planet adjusting to conditions it has not experienced for millions of years. The music of transformation played out across landscapes that have been stable since before human civilization began. In listening to these sounds, we hear not just the death songs of individual glaciers, but the birth cries of a new Earth system, the active processes of contemporary climate, and in which the echo of what we are losing resonates with the uncertainty of what we are becoming. If another ice age comes, what will remain of us? Plastic, steel, radiation, our technofossils may be frozen into strata, confusing future beings who sift through the ruins of a civilization that briefly learned to change the composition of Earth itself. There is something both humbling and disturbing about imagining our cities and technologies preserved in ice for future archaeologists to discover millions of years from now. While the ice ages preserved mammoth hair and ancient pollen with perfect fidelity, they would encounter an entirely different category of remains if they froze a world shaped by industrial civilization. Our technofossils, the artificial materials and synthetic compounds that mark human presence in geological strata, represent a fundamentally new kind of preservation challenge. Objects and substances that have no natural analogues in Earth's deep history. Plastic would be among the most persistent and puzzling of our technofossils. These synthetic polymers, designed to resist degradation and maintain their properties under extreme conditions, could survive in glacial ice far longer than any biological material. Future investigators might find layers of permafrost containing millions of plastic fragments, from microscopic particles that once floated in our oceans to intact bottles and containers that were frozen in the act of decomposing. The chemical signatures of these materials would be unlike anything in the natural world. Synthetic molecules that could only have been created by technological processes operating at industrial scales, that the isotopic signatures embedded in our technofossils would tell stories of nuclear technology and fossil fuel burning that would be immediately recognizable to any scientifically sophisticated civilization. The radioactive isotopes produced by nuclear weapons testing and nuclear power generation have created distinctive signals in materials manufactured during the atomic age, markers that could persist in glacial ice for hundreds of thousands of years. Carbon isotopes from fossil fuel combustion have altered the atmospheric composition in ways that would be preserved in ice core and incorporated into any biological materials that lived during our industrial period. Metals and metal alloys represent another category of technofossil that would be instantly recognizable as artificial. Pure aluminum, refined steel, titanium alloys, and rare earth element concentrations, unlike anything found in natural mineral deposits, would mark the presence of advanced metallurgical technologies. These materials, concentrated in the ruins of our vehicles, buildings, and electronic devices, would create distinctive archaeological signatures that could be detected even if the original artifacts were heavily degraded. Perhaps most intriguingly, our electronic devices contain materials and element combinations that are so unlikely to occur naturally that they would serve as unambiguous markers of technological intelligence. The precise arrangements of silicon, gold, platinum, and rare earth elements in computer chips and circuit boards represent a form of organized matter that natural processes could never produce. Even if individual devices were damaged or corroded, the statistical patterns of element concentrations would reveal the presence of manufacturing processes designed to create specific electronic properties. The synthetic chemicals that permeate industrial civilization would create their own distinctive fossil signatures. Persistent organic pollutants, industrial solvents, pharmaceutical compounds, and synthetic pesticides have molecular structures that are not produced by any known biological or geological processes. These chemical fossils would be preserved in ice and sediments as clear markers of a civilization that had learned to synthesize molecules with properties tailored for specific technological applications. Our concrete and cement structures would create yet another category of technofossil, artificial stone with distinctive crystalline structures and trace element compositions that would clearly indicate manufacture rather than natural formation. The scale of concrete production during the 20th and 21st centuries has been so enormous that future geologists would encounter concrete fragments across entire continental areas, creating a distinctive stratigraphic marker that could be used to identify our geological epoch. The atmospheric modifications we have created through greenhouse gas emissions and industrial processes would be preserved in ice cores as distinctive chemical signatures, unlike anything in the natural record. The rapid increase in carbon dioxide concentrations The presence of synthetic compounds like CFCs and industrial gases, and the altered ratios of atmospheric isotopes would create unmistakable evidence of large-scale technological activity affecting global atmospheric composition. But our technofossils would not be limited to materials and chemicals. The electromagnetic signatures of our civilization, the radio waves, microwave transmissions, and other forms of artificial electromagnetic radiation would also leave traces that could be detected by sufficiently advanced technology. While these signals would not be preserved directly in ice, they would create subtle effects in atmospheric chemistry and potentially in the crystalline structure of ice itself that could serve as evidence of widespread electromagnetic technology. The biological technofossils of genetic engineering would present perhaps the most complex puzzle for future investigators. Genetically modified organisms contain DNA sequences that could not have arisen through natural evolutionary processes, combinations of genes from distantly related species that would be impossible to explain without understanding of advanced biotechnology. If any of these organisms were preserved in permafrost, their genomic signatures would provide clear evidence of deliberate genetic manipulation by technological intelligence. The spatial distribution of our technofossils would also tell important stories about the organization and extent of industrial civilization. The concentration of artificial materials in urban areas, the linear patterns of transportation infrastructure, the regular spacing of agricultural modifications, all of these would create distinctive archaeological signatures that would reveal the systematic nature of technological landscape modification. Perhaps most remarkably, the temporal concentration of our technofossils would mark the Industrial Revolution and its aftermath as one of the most dramatic geological events in Earth's history. The sudden appearance of synthetic materials, radioactive isotopes, and altered atmospheric chemistry in geological strata would represent a transformation as significant as the Great Oxygenation Event or the Cambrian explosion, but compressed into a time span measured in centuries rather than millions of years. Future investigators might also be puzzled by the ephemeral nature of many of our technologies. While some materials would persist for millions of years, others, particularly our information storage systems and electronic devices, would degrade rapidly, leaving behind only trace chemical signatures of their former existence. The irony that our most sophisticated technologies might leave the least durable fossils would create interesting challenges for reconstructing the full scope of our technological capabilities. The discovery of human technofossils in glacial ice would also raise profound questions about the relationship between intelligence and geological time. Our technologies represent solutions to survival and communication challenges that operated successfully for mere centuries before being superseded or abandoned. Future beings examining our technofossils would encounter evidence of rapid technological evolution of solutions to environmental problems that created new environmental problems, of a species that learned to manipulate matter and energy at scales that affected global systems, but that may not have learned to sustain those capabilities over geological timescales. In the end, our technofossils would serve as both monument and cautionary tale, evidence of a species that briefly achieved extraordinary technological capabilities, but that may have been unable to integrate those capabilities with the longer-term stability required for true geological persistence. They would mark us as the first species in Earth's history to become a geological force while still operating within biological timescales, creators of materials that could outlast our civilization by millions of years, while that civilization itself might prove to be only a brief episode in the planet's longer story. The ice that preserves our technofossils would thus become a library of both achievement and limitation, a frozen record of what intelligence can accomplish and what it struggles to sustain when measured against the patient rhythms of geological time. Our thoughts, like ice, hold layers of memory compressed under weight. Dreams, forgotten traumas, and half-remembered moments form deep ice within us, waiting for thaw. And perhaps consciousness itself operates according to the same principles that govern the formation and flow of glaciers. There is something profoundly glacial about the way human memory accumulates and preserves experience. Like snow falling season after season in high mountain valleys, our daily experiences settle into the landscape of consciousness layer by layer, compressing under the weight of subsequent events until they transform from loose, ephemeral impressions into the dense, crystalline structures of long-term memory. The oldest memories, buried deepest in the stratigraphy of the mind, become so compressed and altered that they bear little resemblance to the original experiences from which they formed. Yet they continue to influence the flow and movement of consciousness in ways that operate largely beneath the threshold of awareness. The parallel between glacial formation and memory. Formation extends beyond simple metaphor into the realm of process and structure. Both systems involve the accumulation of material over time, the compression of recent layers by the weight of subsequent additions, and the gradual transformation of accumulated material through processes that operate according to physical and chemical principles. Memory, like ice, exhibits plasticity, the capacity to flow and deform under pressure while maintaining its basic structure and composition. The deepest memories, those formed in early childhood or during periods of intense emotional significance, resemble the basal ice of ancient glaciers, so compressed and altered by time and psychological pressure that their original structure may be unrecognizable. Yet they continue to exert powerful influences on the overall dynamics of consciousness. These foundational memories flow slowly through the psychological landscape, shaping the valleys and ridges of personality, creating the topography across which more recent experiences must navigate. Dreams represent perhaps the most glacial aspect of mental activity, the slow plastic deformation of memory and experience under the pressure of unconscious processing. During sleep, the accumulated material of consciousness flows and shifts according to psychological forces that operate below the level of awareness, carrying fragments of recent experience deep into the interior landscape of the mind, where they encounter older memories and undergo complex transformations. Like glaciers grinding bedrock into new shapes, dreams reshape the cognitive landscape, carving new channels for thought and creating new landforms in the geography of the psyche. The process of forgetting exhibits striking similarities to glacial retreat and ablation. Just as glaciers lose mass through melting and sublimation at their surfaces, while continuing to accumulate material in their upper reaches, memory systems are constantly losing detailed information through forgetting, while simultaneously encoding new experiences. The memories that survive this process of psychological ablation are those that have been compressed into the deepest layers of long-term storage, protected from the erosive effects of time and interference by their depth and density within the cognitive system. Traumatic memories behave like glacial, erratic, large, displaced fragments of experience that have been transported far from their points of origin and deposited in psychological landscapes where they seem alien and incongruous. These memory erratics can remain stable for decades, marking the passage of psychological forces powerful enough to move enormous emotional masses across the terrain of consciousness. Like their geological counterparts, traumatic memories serve as evidence of psychological processes operating at scales and intensities that may be difficult to comprehend from the perspective of normal mental activity. The flow patterns of consciousness exhibit many characteristics of glacial dynamics. Ideas and associations move through the mental landscape following gradients of attention and emotional significance, carving channels of habitual thought that become deeper and more pronounced with use. Creative insights often emerge from the collision of different streams of consciousness, like the crevasses and seracs that form when glacial flows encounter obstacles or merge with other ice streams. Language itself may be understood as a kind of cognitive miranda accumulated, debris of cultural and personal experience that consciousness pushes ahead of itself as it advances through the landscape of communication and meaning. The words and concepts we use carry traces of their origins in other minds and other times, fragments of meaning that have been transported across vast distances in psychological space and deposited in new configurations that reflect the movement and interaction of different streams of consciousness. The phenomenon of insight and sudden understanding resembles glacial calving events, moments when large masses of compressed psychological material suddenly break away from the main body of consciousness and enter the flowing medium of active awareness. These cognitive calving events can be triggered by small changes in mental conditions, just as icebergs can be calved by seemingly minor alterations in temperature or stress within a glacier system. Memory consolidation during sleep appears to follow principles similar to those governing the transformation of snow into glacial ice. The loose, granular structure of recent memories undergoes compression and recrystallization during sleep cycles, with important information being preserved and integrated into long-term storage, while less significant details are allowed to sublimate away. The result is a more compact, stable form of memory that can withstand the pressure of subsequent experiences without losing its essential characteristics. The collective unconscious that Jung described may represent a kind of psychological ice, sheet, vast, slow-moving mass of shared human experience that underlies individual consciousness and influences its flow patterns in ways that may not be immediately apparent. This psychological permafrost contains preserved fragments of ancestral experience, archetypal patterns that have been frozen into the deepest layers of species memory and that continue to influence behavior and cognition even in individuals who have no conscious awareness of their existence. Mental illness sometimes resembles the unstable conditions that lead to glacial collapse. Depression can manifest as a kind of psychological ice age, with normal cognitive flows becoming sluggish or frozen entirely. While mania may resemble the rapid melting and chaotic flow patterns that occur when psychological ice becomes unstable and begins to move too quickly for the landscape to accommodate. The therapeutic process often involves creating conditions that allow frozen psychological material to begin moving again, or helping clients develop more sustainable flow patterns. For emotional and cognitive material that has become unstable, like glaciologists studying ice sheet dynamics, therapists must understand both the surface features of consciousness and the deep structures that govern psychological flow over longer timescales. The aging process affects memory systems in ways that parallel the retreat of glaciers in a warming climate. As cognitive resources decline, the active maintenance of detailed memories becomes more difficult, leading to a retreat of accessible memory toward the most deeply embedded and frequently reinforced material. The memories that survive this cognitive retreat are those that have been most thoroughly compressed into the permanent structure of long-term storage, while more recent and less significant memories may be lost as the psychological climate becomes less capable of sustaining detailed retention. Perhaps most profoundly, consciousness itself may be understood as an emergent property of cognitive glaciation, the result of countless individual experiences accumulating over time and undergoing compression and transformation until they achieve sufficient mass and density to begin flowing according to their own internal dynamics. The self may be nothing more than the particular pattern of flow that emerges when psychological material reaches critical mass and begins to move according to the gradients of attention, emotion, and meaning that define the cognitive landscape. In this glacial model of consciousness, the mind becomes not a computer or a library, but a living geological system, constantly accumulating new material while simultaneously losing older material through various forms of psychological erosion. The thoughts we think and the memories we recall are like the surface features of this cognitive glacier, visible manifestations of vast, slow-moving processes that operate largely outside our direct awareness, but that determine the fundamental contours of our psychological landscape. Understanding consciousness as a glacial system may help us appreciate both its remarkable capacity for preservation and its fundamental dependence on the slow, patient processes that transform experience into the deep structures of memory and meaning that make sustained awareness possible. Picture this moment, if you can, 13,000 years ago, as the last ice age loosened its grip on North America. Something extraordinary was about to happen. A wall of ice, taller than skyscrapers, wider than cities, had been holding back a lake the size of several states combined. Lake Missoula stretched across what we now call Montana, its waters dark and still, waiting behind a dam made entirely of glacier. Then, in a matter of hours, everything changed. The ice began to float. Not slowly, not gradually, but with the sudden buoyancy of something that had reached its breaking point. Water found its way beneath the frozen barrier, lifting it like a cork from a bottle. And when that cork finally gave way, the continent itself would remember. What followed was not a flood in any sense we might imagine from our small human experience of rising creeks or overflowing rivers. This was the earth reshaping itself in real time. 40 cubic miles of water. Imagine trying to hold that number in your mind. Exploded westward across the Columbia River Plateau. The flood moved at highway speeds, carrying boulders the size of houses, carving channels hundreds of feet deep through solid basalt, creating waterfalls that dwarfed Niagara in the space of a few days. These waters sculpted the channeled scablands of Washington state, a landscape so alien that early geologists couldn't believe it had been carved by water at all. They thought it must have taken millions of years. They were wrong by a factor of nearly infinite magnitude. What takes geological ages in our imagination had happened in the time it might take you to drive from coast to coast. But Lake Missoula was not alone in its patient waiting behind ice. Across the northern edges of continents, similar scenes played out as the Ice Age exhaled its final breath. Lake Agassiz in central North America, larger than all the Great Lakes combined, eventually found its way to the sea through what we now call Hudson Bay. When it did, the sudden pulse of fresh water may have disrupted ocean currents, plunging parts of the world back into cold for centuries. These floods speak to something unsettling about the nature of change itself. We imagine transformation as gradual, predictable, something we can prepare for. But ice teaches us otherwise. It shows us that the most profound changes often happen not slowly, but suddenly, after long periods of deceptive stability. The ice holds and holds and holds until one day it doesn't. And then everything we thought we knew about the landscape reveals itself to have been temporary. Standing in the channeled scablands today, you can still read the story written in stone. The fluted cliffs, the hanging valleys, the massive potholes carved by whirlpools that could have swallowed entire forests, all of it testimony to waters that moved mountains and then disappeared, leaving only the scars of their passing. What strikes you most, perhaps, is the silence. These channels that once roared with the sound of a continent draining now hold only wind and sagebrush. The floods that carved them were among the largest in Earth's history, yet they left behind a landscape that feels almost empty, haunted by the memory of water that will never return. And this raises a question that settles into your mind like sediment. If ice can create floods powerful enough to redesign the face of a continent in a matter of days, what other sudden transformations might be waiting, held back by barriers we can't even see? The ice that broke 13,000 years ago had been building pressure for centuries, decades, years. How long does change wait before it refuses to wait any longer? The meltwater floods remind us that the Earth we think we know is always just one breaking point away from becoming something entirely different. And yet, as we'll discover, even these catastrophic waters were just one note in a larger symphony of loss, one voice in the great silence that was about to swallow an entire world. There was once a place that no longer exists anywhere on Earth, not in fragments, not in protected valleys or forgotten corners. It is as gone as Atlantis, as vanished as last year's snow. But unlike the mythical cities of our imagination, this lost world was real, and it covered more of our planet's surface than any other ecosystem in Earth's history. They called it the Mammoth Steppe, though it was neither steppe as we understand it today, nor defined entirely by mammoths. It was something else entirely, a vast, cold grassland that stretched from Spain to Alaska, from Scotland to China, an unbroken carpet of life that supported more large animals than the African savanna at its richest. For hundreds of thousands of years, this was the dominant ecosystem on Earth, home to creatures that seem mythological to us now. Woolly rhinoceros with horns like curved swords, cave lions larger than any cats alive today, giant bears that could look a human in the eye while standing on all fours, and the mammoths. Always the mammoths. But here's what haunts scientists who study this lost world. It didn't disappear gradually. It didn't fade away as climates slowly shifted or predators slowly multiplied. In geological terms, it vanished almost overnight. 12,000 years ago, this ecosystem that had dominated the planet suddenly collapsed, taking with it not just individual species, but entire ways of being alive. Today, we find their ghosts everywhere. In the permafrost of Siberia, mammoth tusks emerge each summer like strange harvests, so common that they support an entire ivory trade. DNA extracted from these remains has allowed scientists to sequence complete mammoth genomes, to understand their family relationships, to trace their slow retreat across the continents as the world warmed. Some of these genetic ghosts are so fresh, so complete, that scientists have seriously proposed bringing mammoths back. But should they? In a laboratory in Boston, researchers are editing the genes of Asian elephants, inserting mammoth DNA sequence trait by trait. They speak of resurrection as if it were simply a technical challenge, a problem to be solved with enough funding and determination. Cold tolerance genes, thick coat genes, the precise curve of tusks encoded in nucleotides. They're creating something that has never existed, not quite mammoth, not quite elephant, but something new that carries the genetic echo of the disappeared. Yet the more we learn about the mammoth steppe, the more complex this ghost becomes. The mammoths weren't just animals grazing on an ancient grassland. They were architects of their own world. Their enormous feet, their constant movement, their habit of knocking down trees and trampling vegetation, all of this maintained the grassland ecosystem. Without mammoths, forests began to grow. Without the open grassland, the smaller animals disappeared. Without the smaller animals, the predators vanished. It was an ecosystem held together by giants, and when the giants fell, everything fell with them. The question that keeps paleontologists awake at night is this: what really killed the mammoth steppe? Climate change was certainly involved. As the Ice Age ended, forests began to replace grasslands. But humans had also spread across these landscapes, armed with spears and fire, and an intelligence that could track the largest animals across continents. Some scientists argue for climate, some for hunting, some for a combination of both. The truth, like the ecosystem itself, may be lost forever. What we do know is that the traces remain, written in languages we're still learning to read. In the genes of modern elephants, mammoth ancestry whispers through millions of years of evolution. In the stories of indigenous peoples across the Arctic, creatures that sound suspiciously like mammoths populate mythologies passed down through generations. In the dreams of some children who draw pictures of furry elephants they've never seen, as if some ancestral memory still moves through us. The de-extinction projects continue. Mammoth calves may walk the earth again within our lifetimes. Engineered creatures carrying the genetic memories of their predecessors. but they would be walking on a planet that no longer contains the world that made them. The mammoth steppe is gone, replaced by forests and farms and cities. These new mammoths would be orphans of time, citizens of nowhere, carrying genes adapted for a world that exists now only in permafrost and imagination. Perhaps that's as it should be. Perhaps some ghosts are meant to remain ghosts, and some lost worlds should stay lost. Or perhaps the very act of remembering, of trying to understand what we've lost, is itself a kind of resurrection, not of flesh and blood, but of wonder, of the recognition that this planet has held forms of beauty we can barely imagine, standing in the tundra today, where mammoth bones still emerge from the thawing ground. You might close your eyes and try to picture it, endless grasslands under vast skies, herds of giants moving like clouds across the horizon, the ground trembling under feet that will never touch earth again. The silence that replaced their footsteps is perhaps the deepest silence our planet has ever known. And yet, in that silence, if you listen carefully, you might hear something else approaching the patient, inexorable advance of another kind, of giant, one that moves not on feet, but through time itself. There are forces on this planet that announce themselves with fury, earthquakes that split the ground in seconds, volcanoes that paint the sky red in a single night, tsunamis that remake coastlines in hours. But ice is not one of these forces. Ice is patient. Ice waits, footstep forward. Yet, for all its patience, ice may be the most violent force our planet has ever known. Consider the Laurentide ice sheet, the great wall of frozen water that once covered most of Canada and much of the northern United States. At its peak, this single glacier contained more ice than exists today in all of Antarctica and Greenland combined. It rose to miles into the sky, a frozen mountain range that stretched from coast to coast. It ate the landscape, the rock beneath the ice, billions of years old, stone that had survived meteor impacts and volcanic eruptions and every catastrophe Earth could imagine. This ancient rock bent under the weight of ice like clay in a child's hands. The entire continental crust sank down, 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 pressed into the softer mantle below by the sheer mass of water frozen into crystal. Even today, 20,000 years after that ice began to melt, the land is still rising, still recovering, stood up. Imagine a force so powerful it can pluck mountains from their roots and carry them hundreds of miles, then drop them casually in new locations, like a child abandoning toys. The Canadian Shield, that ancient heart of the North American continent, was strip-mined by ice. Billions of tons of rock scraped up and transported south, ground into powder by the slow violence of glacier movement. This is how we get the rich farmland of the American Midwest, not from any kindness of climate or accident of geography, but from the patient destruction of Canada. The ice sheet acted like a massive conveyor belt, carrying the pulverized remains of northern mountains south, spreading them across what would become some of the most fertile soil on Earth. Every cornfield in Iowa, every wheat field in Kansas, grows in dirt that was once the bedrock of Hudson Bay, transported grain by the most patient destroyer our planet has ever known. The scars are everywhere if you know how to look. Long Island, Cape Cod, Martha's Vineyard, these aren't permanent features of the coast, but piles of debris bulldozed into place by advancing ice, then abandoned when the glaciers retreated. The Finger Lakes of New York are trenches carved by ice fingers pressing into the earth like a giant hand grasping for purchase. The thousands of lakes that Minnesota and Wisconsin are footprints left by buried ice blocks. Profound violence of ice is temporal. It doesn't just reshape landscapes, it reshapes time itself. A single advance of ice can erase millions of years of slow river carving, patient wind erosion, the gradual work of water finding its way to the sea. What takes eons to build, ice destroys in millennia. What took the patient collaboration of countless small forces to create, ice unmakes with the simple persistence of its weight. The Great Lakes themselves are perhaps the finest example of this temporal violence. Before the ice came, this region was drained by rivers flowing in entirely different directions, following valleys carved over millions of years by the slow collaboration of water and gravity. The ice sheets scraped all of this away, carving new basins, redirecting rivers, creating an entirely new geography, but a fundamentally different world. And the ice remembers everything it destroys. Glacial tiltha, mixed debris left behind by retreating ice, contains rocks from thousands of miles away, fossils from creatures that lived millions of years apart, minerals from mountains that no longer exist. It's as if the ice sheets were keeping a geological diary, collecting samples of everything they encountered on their slow journey across continents. Standing today at the edge of a remaining glacier in Alaska, in Greenland, in the high peaks of mountain ranges, you can watch this violence in action. Not the dramatic calving of icebergs into the sea, though that too is part of the story, but the quieter, more persistent grinding. Listen carefully, and you might hear it. The sound of rock being crushed to powder, of boulders being pushed like pebbles. We live such brief lives that we can't perceive the movement, can't feel the pressure building, can't see the slow rearrangement of countenance beneath our feet. To us, ice seems static, peaceful, almost benign, but ice is never still. Even when it appears motionless, it's flowing like water, just water so cold and thick that its movement can only be measured in years and decades rather than seconds and minutes. This is perhaps why we struggle to understand our current moment. The ice that remains on our planet, in Greenland, in Antarctica, in the high mountain glaciers, contains violence on a scale that dwarfs our human capacity for destruction. If all of it melted, sea levels would rise by more than 2 feet, coastal cities would vanish, entire nations would disappear beneath waves. But this would not happen overnight, or even over decades. It would be ice expressing its violence in the only way it knows how, slowly, patiently, inexorably. The ice sheets that once covered much of North America and Europe are gone now, reduced to stories told in stone and till. But their departure has left us with a question that hangs in the air like frost in a world. What happens when patience finally ends? The answer, perhaps, lies not in the future of ice, but in what ice has been preserving all along, locked away in frozen vaults that are only now beginning to open. There are places on Earth where time stops, not metaphorically, not poetically, but literally, where the normal processes of decay and decomposition cease, where the past is held in suspension like an insect in amber, waiting for the moment when warmth will wake it from its frozen sleep, We call these places permafrost, but that name barely hints at their true nature. These are libraries of ice, archives of everything that lived and died in the North during the thousands of years when cold ruled the world. Each layer contains the dreams of a different decade, a different century, a different millennium. Seeds that sprouted in meadows where musk oxen grazed, pollen from flowers that bloomed under midnight suns, leaves that fell from trees whose species exist now only in these frozen pages, and sometimes something more extraordinary. In 2012, Russian scientists extracted seeds from the permafrost of Siberian arrow-leafed campion seeds that had been frozen for over 30,000 years. 30,000 years. These seeds had been stored in underground chambers by Arctic ground squirrels during the last ice age, then forgotten as the squirrels died and the chambers filled with ice. For 300 centuries, these seeds waited in the cold darkness. Their cellular machinery slowed to near stillness, their potential for life held in perfect suspension. When the scientists warmed them, grew flowers that had last bloomed when Neanderthals still walked the earth, burst into white petals in a Moscow laboratory. The DNA had remained so perfectly preserved that these ancient plants could reproduce, could create new seeds, could continue a genetic conversation that had been interrupted by 30,000 years of winter. But seeds are not the only dreams locked in permafrost. There are mammoths so perfectly preserved that their stomach contents are still identifiable. Buttercups and grasses that they ate for lunch on a day 40,000 years ago, before lying down for what they must have expected to be a brief nap. There are insects with their wings still outstretched, frozen in the act of flight. There are tree trunks that still show the bite marks of beavers, the wood unratted, the tooth marks as fresh as if they were made yesterday. Each of these preserved moments is a kind of time travel, a window into worlds that existed long before human memory began. In permafrost, we find not just the remains of life, but life itself, dormant, waiting, dreaming of warmth. Bacteria that infected mammoths still carry their ancient genes. Viruses that jumped between species in Ice Age ecosystems remain infectious, ready to resume their microscopic campaigns in a world they might no longer recognize. This preservation is so complete, so perfect, that it challenges our understanding of what death means. Are these 30,000-year-old seeds alive or dead? What about the bacteria that can still reproduce after eons of frozen sleep? Where is the line between life and dormancy, when dormancy can last longer than entire mountain ranges? The Yucca mammoth, discovered in the Siberian permafrost in 2010, died at least 39,000 years ago. Yet her blood still flows liquid from her veins when researchers thaw her remains. Her cells are so perfectly preserved that scientists have successfully extracted DNA, mapped her genome, traced her family relationships to mammoths that died tens of thousands of years before her. Died, she has simply been waiting. Indigenous peoples of the Arctic have always known about these frozen archives. For generations, they have told stories of creatures emerging from the ice, sometimes bones, sometimes flesh, sometimes what appeared to be sleeping giants. Western science dismissed these accounts as folklore until European explorers began to encounter the same phenomena. Entire carcasses of extinct animals emerging from riverbanks, so fresh they could be fed to sled dogs. But now the permafrost is changing. Temperatures across the Arctic are rising twice as fast as the global average, and the frozen libraries of the North are beginning to thaw. Each summer, more artifacts emerge, stone tools that hunter-gatherers dropped during brief Ice Age summers, wooden vessels carved by hands that have been dust for millennia, textiles woven from the hair of animals that no longer exist in Alaska. Entire villages are relocating as the permafrost beneath them melts, destabilizing the ground that their ancestors assumed would remain frozen forever. In Siberia, massive craters are opening as underground ice melts and the land collapses, releasing trapped gases that have been locked away since the Pleistocene. The dreams in permafrost are waking up all at once after their long sleep. Some of what's emerging is beautiful. Flowers that haven't bloomed for 30,000 years. Seeds that carry the potential for resurrection of entire ecosystems. But some of it is dangerous. Anthrax spores, dormant for decades in the carcasses of reindeer, have infected modern herds when thawing permafrost exposed old burial sites. Viruses that infected Ice Age mammals remain viable, their genetic material intact, their pathogenic potential unknown. Scientists estimate that there may be hundreds of thousands of years worth of carbon stored in permafrost worldwide. Carbon that was absorbed from the atmosphere by plants and animals during the Ice Ages, then locked away in the Great Freezer of the North. As permafrost thaws, this carbon is released back into the atmosphere as carbon dioxide and methane, accelerating the very warming that's causing the thaw. But perhaps the most profound dreams locked in permafrost are the ones we haven't discovered yet. Entire ecosystems that thrived during brief, warm periods between ice ages, then vanished when the cold returned. Evidence of early human presence in the Arctic, tools and art and shelter, remains that could rewrite our understanding of how our species survived the ice. Genetic material from creatures we can't even imagine. Species that lived and died without leaving any trace except these frozen fragments, standing at the edge of a thawing permafrost bank, watching ancient ice melt into modern rivers, carrying the dreams of dead millennia toward the sea. You begin to understand something fundamental about the nature of preservation and loss. These frozen archives have kept perfect records of worlds we thought were lost forever. But preservation, it turns out, depends on cold, and cold, we're learning, is not permanent. The permafrost is teaching us that nothing stays buried forever. Every dream we think we've lost, every past we think we've left behind, is simply waiting for the right temperature to wake it up. And now, as the planet warms, as the great libraries of ice begin to melt, we're about to discover what dreams we've been sleeping on, what memories we've been standing on, what futures we've been unconsciously preparing for in the vast, frozen archives beneath our feet. But to understand why this thawing matters so much, we need to remember how close we came to being frozen dreams ourselves. There is a moment in our species' history that almost didn't happen, a moment when the entire future of human consciousness, art, language, love, and wonder balanced on the edge of extinction, like morning frost that could either melt into another day or never see sunlight again. 70-3,000 years ago, Mount Toba erupted in what is now Indonesia. This was not a normal volcanic eruption. the kind that makes news for a week and then fades from memory. This was a supervolcanic explosion that ejected more than 670 cubic miles of rock and ash into the atmosphere, darkening skies across the entire planet. The ash fell for weeks, then months, covering the ground in a gray shroud that stretched from Southeast Asia to Africa. But the ash was just the beginning. For years afterward, the sun was dimmed by volcanic particles. Suspended in the atmosphere, global temperatures dropped by as much as 21 degrees Fahrenheit. Forests died. Rivers froze. The world entered what scientists call a volcanic winter that may have lasted for decades. And somewhere in Africa, our ancestors' perhaps as few as 10,000 individuals, maybe fewer, huddled around fires that might have been the only points of light in a darkened world, trying to survive what could have been the end of our story before it had properly begun. Genetic evidence suggests that the human population crashed during this period, shrinking to numbers so small that every person alive today descends from this tiny group of survivors. We are all children of the few who refused to surrender to the cold, who kept their fires burning through the long volcanic night, who told stories and sang songs and made love and had children even when the world seemed to be ending around them. Living through ice ages meant living always with the knowledge that survival was temporary, that warmth was borrowed time, that the edge of extinction was never more than one bad winter away. Our ancestors developed technologies not for comfort but for persistence, the controlled use of fire, the construction of clothing from animal skins, the creation of shelters that could hold heat through months of darkness. But perhaps more importantly, they developed psychology for survival, the ability to cooperate in small groups, to share resources during scarcity, to plan for futures they might not live to see, the capacity to find meaning in hardship, to create art and music and ritual, even especially when existence itself was precarious. Cave paintings from the ice ages show us people who understood they were living at the margins of possibility. These aren't pictures of conquest or dominance, but of observation, of careful attention to the animals and landscapes that meant the difference between survival and disappearance. The artists who painted mammoths and bison and reindeer on cave walls by flickering firelight were creating more than art. They were making maps of resources, prayers for successful hunts, teaching tools for children who would need to know which animals could be tracked, which could be trusted, which could be transformed into food and shelter and life. Archaeological evidence suggests that during the worst periods of glaciation, human populations retreated to refuges, pockets of relatively warmer climate where life could persist while ice covered the majority of the world. Southern Spain, parts of Italy, isolated valleys in the Caucasus Mountains, these became the Noah's Arks of human consciousness, preserving not just bodies but cultures, languages, technologies, stories. The people who survived in these refuges developed what we might call Ice Age wisdom, the knowledge that abundance is temporary, that every warm day is a gift, that survival depends not on individual strength but on collective memory. They became experts at reading subtle changes in weather, at finding food in landscapes that appeared barren, at making tools from whatever materials the cold world provided. But survival at the margins also meant living with loss, How many languages died when their last speakers froze? How many technologies were lost when the people who knew them couldn't make it through another winter? How many songs, stories, ways of understanding the world simply vanished into the cold silence of glacial nights? The humans who survived the ice ages were not the same species that had entered them. Not biologically remained Homo sapiens, but culturally, psychologically, spiritually. They emerged from the cold with a different relationship to time, to scarcity, to the fragility of existence. They had learned that civilization is not a destination, but a process, not a permanent achievement, but something that must be maintained, generation after generation, against forces that would gladly erase it. Perhaps this is why we retain such deep, unconscious memories of cold and darkness, why winter still triggers something primal in our nervous systems, why stories of long nights and endless winters resonate in our mythologies across cultures that never experienced ice ages directly, why we hoard food, why we gather around fires, why we tell stories to children who will face their own uncertainties. The edge of survival leaves marks not just on bones, but on DNA, not just on individuals, but on entire species' ways of being in the world. Modern humans carry genetic variants that helped our ancestors survive extreme cold, metabolize scarce food sources, resist diseases that thrived in ice age conditions. We are walking archives of adaptation, living libraries of survival strategies, tested against the worst conditions our planet could provide. But we also carry something else from those ice age refugia, the knowledge that warmth returns, that even the longest winter eventually gives way to spring, that survival is possible, not just individually, but collectively, not just physically, but culturally, that humans can adapt not just by changing themselves, but by changing their environment, making fire, building shelters, creating communities that can preserve knowledge and values and hope through any amount of darkness. Standing today in the warmth of our current interglacial period, surrounded by technologies that would seem like magic to our Ice Age ancestors, it's easy to forget how recently we were refugees from cold, how narrowly we escaped being just another species that couldn't adapt to changing conditions. But the ice remembers. The ice is always waiting at the edges of warmth, patient and persistent, ready to test once again whether consciousness and culture and love are strong enough to survive another round of selection. Our ancestors passed that test barely by firelight, in caves wrapped in furs and hope and each other's stories. The question that hangs in our warming air is whether their descendants have inherited not just their genes, but their wisdom, the knowledge that survival depends not on avoiding the edge, but on learning how to live there gracefully, how to find meaning and beauty and connection, even when the world seems determined to erase us. Because the edge of survival, it turns out, is not a place we visited once in our distant past. It's where we've always lived, where we still live, where we will always live, balanced between existence and extinction, between the fire we've learned to tend and the darkness that surrounds it. We live in the space between ice ages, like flowers blooming in the brief warmth between eternal winters. Our entire human civilizationary city we've built, every field we've planted, every story we've told us existed within what geologists call the Holocene. A warm period that began roughly 11,700 years ago and has provided the stable climate foundation for everything we consider normal about life on Earth. But here's what keeps climatologists awake at night. Interglacials, like ours, typically last between 10,000 and 20,000 years. We're already past the midpoint of what might be expected for a natural warm period. By the deep rhythm of ice ages that has governed our planet for the last 2.5 million years, we should be preparing for the gradual return of ice. Instead, we find ourselves in unprecedented territory. The carbon dioxide levels in our atmosphere have risen higher than they've been in more than 3 million years, long before ice ages began their regular cycles across the northern continents. We've added more greenhouse gases to the atmosphere in the last 2 centuries than natural processes typically release in tens of thousands of years. We've changed the chemistry of the air so dramatically that we've entered what scientists call the Anthropocene, the age when human activity becomes a geological force comparable to volcanoes and ice sheets and the movement of continents. This should be reassuring. After all, if ice ages are our planet's default state, and if human activity is warming the climate, then perhaps we've solved the problem of future glaciation. Perhaps we've bought ourselves permanent summer, permanent warmth, permanent freedom from the slow violence of advancing ice. But the Earth's climate system is not a thermostat we can simply adjust. It's more like a vast, interconnected web of feedback loops, tipping points, and non-linear responses that we're only beginning to understand. And ice, it turns out, has its own ways of responding to warming that don't follow the simple logic of hot versus cold. Consider Greenland, that vast island covered by ice that's nearly 2 miles thick in places. This ice sheet contains enough frozen water to raise global sea levels by more than 20 feet if it melted completely. For most of human history, Greenland's ice has been stable, growing from snowfall in the interior while losing ice around the edges in a roughly balanced exchange. But in recent decades, something has changed. The ice sheet is now losing mass faster than it gains it, contributing to rising sea levels around the world. What's particularly unsettling is how this melting accelerates. As ice melts, it reveals darker rock and soil beneath, which absorbs more sunlight than white ice, which causes more melting, which reveals more dark surface, which absorbs more heat. It's a feedback loop that once started becomes increasingly difficult to stop. The ice doesn't melt gradually and predictably, it melts in sudden pulses, in unexpected surges, in ways that surprise even the scientists who study it. Antarctica presents an even more complex puzzle. While some parts of the Antarctic ice sheet are growing thicker due to increased snowfall, other parts are melting rapidly, particularly where the ice meets the warming ocean. The West Antarctic ice sheet, which contains enough water to raise sea levels by more than 10 feet, sits largely below sea level, held in place by ice shelves that float on the ocean. As these ice shelves melt from below due to warming seawater, they become less able to hold back the land-based ice behind them. Some scientists worry about what they call ice cliff instability, a process where once it begins, the collapse of ice sheets could accelerate dramatically, much faster than current models predict. Ice cliffs more than about 200 feet tall become unstable under their own weight and begin to collapse into the ocean. This creates higher cliffs behind them, which also become unstable, which creates even higher cliffs, and so on in a cascade that could drain massive ice sheets in centuries rather than millennia. But ice is not the only system responding to our warming world in unexpected ways. The great ocean currents that redistribute heat around the planet, currents that keep Europe warm despite its northern latitude, that bring nutrients to ocean ecosystems, that drive weather patterns around the globe. These currents are slowing down as fresh water from melting ice dilutes the salty water that drives their circulation. The Gulf Stream, which carries warm water from the Caribbean to the North Atlantic, has weakened by about 15% since the 1950s. If it continues to slow, or if it reaches a tipping point where it shuts down entirely, Europe could cool dramatically, even as the rest of the world warms. Paradoxically, global warming could trigger regional cooling, creating climate chaos that makes ice age fluctuations seem gentle by comparison. Perhaps most unsettling of all is the awakening of the permafrost. As we explored earlier, the frozen soils of the Arctic contain vast stores of carbon that was removed from the atmosphere over hundreds of thousands of years and locked away in the great freezer of the North. As temperatures rise and permafrost thaws, this carbon is being released back into the atmosphere as carbon dioxide and methane, accelerating the very warming that caused the thaw. Scientists estimate that permafrost contains twice as much carbon as currently exists in the entire atmosphere. Even a partial thaw could release enough greenhouse gases to push the climate system past tipping points from which recovery might take thousands of years. We could trigger changes that continue long after we've stopped adding carbon to the atmosphere, changes that unfold according to their own internal logic rather than our intentions. Standing in this moment, balanced between the ice ages of our past and the uncertain climate of our future, we find ourselves in a position that no species has ever occupied. We have become the asteroid, the supervolcano, the ice sheet of force of nature capable of changing the planetary conditions that allowed us to evolve in the first place. But we are also the first species capable of understanding what we're doing, the first to study ice core and read the history of past climates, the first to model future conditions and recognize tipping points before we cross them, the first to face a planetary crisis with the knowledge and technology to potentially address it. The fragile balance of today exists not just in our climate system, but in this tension between our power to destroy and our capacity to understand, between the speed of our impact and the wisdom needed to guide it. We are living through what might be the most important few decades in the history of complex life on Earth. Decades when we discover whether intelligence and cooperation can evolve faster than the consequences of our previous actions. The ice ages teach us that change, when it comes, often comes suddenly, that stability is temporary, that the conditions we consider normal are actually extraordinary. But they also teach us that life persists, that adaptation is possible, that even the most extreme changes create new opportunities for those clever enough to recognize them. The question hanging in our warming air is not whether the climate will change. It's already changing. The question is whether we can change with it, whether we can learn to live gracefully in a world that no longer follows the rules we thought we understood, whether we can build civilizations flexible enough to bend with whatever wind may come. And as we ponder this question, as we measure rising seas and melting ice and shifting weather patterns, we might ask ourselves, what if the changes we're witnessing today are not the end of the story, but a return to something much older? What if the deep rhythms of ice and warmth hold secrets about human history that we've barely begun to uncover? Imagine, for a moment, that everything we think we know about human history represents only the final chapter of a much longer book. Imagine that the civilization we call the beginning Mesopotamia, ancient Egypt, the first cities where, actually, the rebuilding, the recovery, the slow crawl back to complexity after something much older was lost beneath rising seas and forgotten beneath accumulating millennia. This is not the speculation of fringe archaeologists or ancient alien theorists. This is the kind of question that keeps mainstream scientists awake at night, staring at maps of the ocean floor and wondering what stories might be written in the sediment of drowned coastlines. During the last ice age, sea levels stood nearly 400 feet lower than they do today. Imagine that, for a moment, 400 feet. Entire continental shelves that are now underwater were dry land, vast plains, and river valleys where early humans could have lived, developed sophisticated cultures, built settlements that would make our current archaeological finds look like scattered footnotes. The Bering Land Bridge that allowed humans to first enter North America was just one small section of a much larger world of exposed continental shelf. Between Asia and Australia, dozens of islands were connected by dry land. The Persian Gulf was a river valley. The English Channel was a plain where mammoths grazed. The entire geography of human possibility was different. Larger than anything we can see today. As the Ice Age ended and sea levels rose, all of this disappeared beneath the waves, not gradually, not gently, but sometimes in catastrophic pulses as ice dams broke and glacial lakes drained into the oceans. The meltwater pulse 1A, about 14,000 years ago, raised global sea levels by more than 50 feet in just a few centuries. Entire landscapes vanished. If humans had built cities on those landscapes, developed agriculture in those river valleys, created complex societies along those coasts, all evidence would now lie beneath hundreds of feet of water and thousands of years of marine sediment. But here's what makes this speculation more than wishful thinking. We keep finding evidence that human sophistication goes back much further than we used to believe. Göbekli Tepe in Turkey, built 11,000 years ago, predates Stonehenge by 6,000 years and the pyramids by 7,000 years. It represents a level of social organization and symbolic thinking that archaeologists didn't think existed so early in human history. If humans could build Göbekli Tepe 11,000 years ago, what might they have built 12,000 years ago, 15,000 years ago, 20,000 years ago? The flood myths that appear in cultures around the world, from the biblical Noah to the Sumerian Gilgamesh to Native American creation, stories all speak of a time when rising waters transformed the world. Traditional archaeology has dismissed these as primitive attempts to explain natural phenomena. But what if they're cultural memories of actual events? What if these stories preserve the oral history of civilizations that watched their world disappear beneath rising seas. Genetic evidence adds another layer to this mystery. DNA studies show that human populations underwent a series of bottlenecks and expansions that don't quite match the simple story of gradual dispersal from Africa. There are signs of much older migrations, much earlier developments of population centers, much more complex patterns of human movement than we can explain with the archaeological record we've found so far. And then there are the anomalies. Structures found underwater off the coasts of Japan, India, and the Mediterranean that appear too regular, too geometric, too intentional to be natural formations. Most are dismissed as misidentified rock formations or wishful thinking. But some researchers wonder, what if they're not? The Yonaguni Monument off the coast of Japan, discovered in the 1980s, consists of massive stone terraces, perfectly straight edges, and right-angle corners that extend for hundreds of feet underwater. Geologists argue it's a natural formation carved by water and wind over millions of years. Marine archaeologists point to features that look suspiciously like stairs, roads, and carved symbols. The debate continues, but the structure remains. 80 feet below the surface, in water that has covered it for at least 10,000 years. Off the coast of India, marine archaeologists have discovered what appear to be the remains of cities in the Gulf of Kamhat. Submerged structures that carbon dating suggests are over 9,000 years old. Ancient Tamil literature speaks of Kumari Kandam, a lost continent that was gradually consumed by rising seas. Could these underwater structures be the remnants of settlements described in myths and legends? But perhaps the most intriguing evidence comes not from what we've found, but from what we haven't found. The archaeological record of human development shows sudden leaps in sophistication that are difficult to explain. Rapid development of agriculture in multiple locations around the world. The sudden appearance of complex astronomical knowledge in early civilizations. The sophisticated mathematical concepts that seem to emerge fully formed in cultures that supposedly had no prior experience with such abstractions. What if these leaps represent not innovation but rediscovery? What if the humans who survived the Ice Age melting carried with them not just genes and basic survival skills, but fragments of much older knowledge? What if agriculture wasn't invented, but remembered? What if astronomy wasn't discovered, but reconstructed from cultural memories of people who had once studied the stars from observatories that now lie beneath the sea? The speculation becomes even more tantalizing when we consider the scale of what was lost. The continental shelves that are now underwater represent millions of square miles of potentially habitable land. If human population density on those shelves was similar to what archaeologists find in inland areas from the same period, we might be missing evidence of millions of people, entire civilizations whose existence has been erased by rising seas. Some researchers have begun using new technologies to peer beneath the ocean floor, mapping buried river valleys and ancient coastlines, looking for the kinds of geological features that attract human settlement. They're finding river deltas, natural harbors, and freshwater source atoll, all exactly the kinds of places where complex societies might have developed. But even if sophisticated civilizations existed on the exposed continental shelves during the Ice Age, even if rising seas did erase vast chapters of human history, would we ever be able to prove it? The ocean is not kind to archaeological evidence. Wood rots, metal corrodes, organic materials disappear. Only the most durable material, stone, ceramics, perhaps metal objects in very specific conditions, would survive 10,000 years underwater. And so we're left with speculation, with tantalizing hints, with questions that may never be fully answered. Did human civilization rise and fall and rise again, like the ice ages themselves? Are we the inheritors not just of biological evolution, but of cultural evolution that stretches back much further than we imagine? Are the myths and legends of lost worlds not fantasies but memories, standing on a modern beach, watching waves break where forests once grew, where rivers once flowed, where people might once have lived and loved and built and dreamed? You begin to understand that absence of evidence is not evidence of absence. The ocean keeps its secrets. The ice ages took their witnesses with them when they retreated, and we are left to wonder what stories the water might tell, if only we knew how to listen. Perhaps that's fitting. Perhaps every civilization is destined to wonder about the ones that came before, to search for ancestors in the gaps of the archaeological record, to look for meaning in the spaces between what we know and what we can prove. Perhaps the search itself is more important than the finding, the wondering more valuable than the certainty. But as we wonder about lost histories, as we speculate about civilizations beneath the waves, we might also ask, what will the archaeologists of the future make of us? What will survive of our cities, our technologies, our stories, when the next great change comes? And it will come not ice, perhaps, but something else, some other transformation that will render our world as foreign and inaccessible as the drowned shelves of the Ice Age world. For now, though, in this brief, warm moment between whatever was and whatever will be, we have the luxury of speculation, the privilege of wonder, the opportunity to imagine that we are part of a story much larger and more complex than the few thousand years we can document with certainty. And perhaps, in the end, that imagination is itself a kind of inheritance from whoever came before, a gift from the deep past that survives even when everything else has been claimed by time and tide. There is a particular quality of silence that comes after great transitions, a quiet so profound it seems to have weight, substance, presence. It's the silence of snow-covered cities after a blizzard has passed, the silence of forests after wildfire, the silence of beaches after storms. But perhaps no silence is as complete, as final, as the silence that follows the retreat of ice, when the great ice sheets began their withdrawal 20,000 years ago. They left behind a world that had never existed before, not a return to pre-condition shows, landscapes. Those ecosystems, those ways of being alive, had been scraped away, ground to powder, transported thousands of miles, and deposited in new configurations. What emerged from beneath the melting ice was virgin territory, blank pages in the book of Earth, waiting for life to write new stories. Imagine standing in what would become the Great Lakes region as the last ice finally melted. The landscape around you would be raw, scraped clean, pocked with thousands of temporary lakes trapped behind moraines and debris, no soil deeper than what the ice had recently deposited, no forests, no grasslands, no established ecosystems. just rock and gravel and mud and the sound of meltwater finding its way toward the sea through channels that had never existed before. The silence in such a place would be almost total. No bird songs, there were no birds yet, no trees for them to nest in, no insects for them to eat, no rustle of wind through Levsphere were no leaves, no calls of large mammals hadn't arrived yet, were still following the retreating ice northward or moving up from refugia in the south. Just the sound of water dripping, flowing, pooling, and underneath that, a quiet so deep it would seem like the planet itself was holding its breath. But silence, it turns out, is not empty. Silence is potential, and into that post-glacial quiet came life, tentatively at first, then with increasing confidence and complexity. Pioneer species, adapted for rapid colonization of disturbed areas, arrived first. Arctic willows and birches, spreading from seeds carried by wind or by the few. Animals that had survived the Ice Age in nearby refugia. Mosses and lichens, those patient architects of soil, beginning the slow work of building substrate for more complex plants. The process was not uniform. Some areas, blessed with better drainage or protection from wind, developed forests within centuries. Others remained tundra for millennia. Some lakes filled with sediment and became marshes, then meadows, then forests. Others deepened and clarified, becoming the clear, cold lakes we know today. Each location followed its own trajectory, its own story of succession and development. What's remarkable is how quickly this happened in geological terms. Within a few thousand years, landscapes that had been under ice for 100,000 years were supporting complex ecosystems. Caribou and moose moved north, following the advancing forests. Wolves followed the herbivores. Birds arrived, bringing seeds in their digestive systems, accelerating the spread of plants. Beavers engineered wetlands that created habitat for dozens of other species, but the silence never completely disappeared. It lingered at the edges, in the spaces between notes of the slowly developing symphony of life. And those who pay attention can still hear it today, particularly in the far north, where the retreat of ice is still visible in the landscape, still audible in the absence of sounds that have not yet learned to exist there. The Inuit have words for different qualities of silence, different textures of quiet that emerge in different seasons, different weather conditions, different stages of ice formation and melt. They understand that silence is not the absence of sound, but the presence of space, the availability of acoustic territory for whatever might choose to fill it. In the high Arctic, where ice still dominates the landscape for much of the year, this understanding becomes visceral, immediate, essential for survival. But the silence after ice retreat is not just acoustic. It's also ecological, cultural, evolutionary. The mammals that returned to post-glacial landscapes were different from the ones that had lived there before the ice. Giant ground sloths, short-faced bears, American cheetahs, these had gone extinct during or shortly after the Ice Age. The returning fauna was smaller, more adaptable, more able to survive in a world where climate could change rapidly and resources could become scarce without warning. The humans who moved into these post-glacial landscapes were also different from their ancestors who had survived the Ice Age in refugia. They carried new technologies, new social organizations, new ways of understanding and relating to the world. They were the inventors of agriculture, the builders of the first permanent settlements, the creators of the first complex civilizations. In some sense, they were filling the silence left by the retreat of ice with the first tentative notes of what would become human history as we know it. Yet, even as life returned to the post-glacial world, even as forests grew and animals flourished, and humans began their remarkable expansion across the newly available landscapes, something remained missing. The megafauna that had defined Ice Age ecosystems, mammoths and mastodons, the giant beavers and dire wolves, the saber-toothed cats and cave bears were gone. Their silence was permanent, their absence a kind of negative space that shaped everything. That came after modern ecologists used the term ghost of predation past to describe the behaviors that many plants and animals retain, even though the predators that shaped those behaviors are extinct. Honey locust trees still produce thorns capable of deterring browsers larger than any that exist in North America today. Ground sloths were the last large mammals capable of eating honey locust pods and dispersing the seeds. The trees are still defending against ghosts, still producing thorns for animals that will never return. This ghostly presence of the absent megafauna may be one of the most profound aspects of post-glacial silence. We live in ecosystems that are still shaped by creatures that no longer exist, still responding to selective pressures that vanished thousands of years ago. The silence contains not just the absence of sound, but the absence of ecological relationships, evolutionary partnerships, ways of being alive that took millions of years to develop and only decades to disappear. Perhaps this is why certain landscapes still feel haunted, still carry a sense of incompleteness that we can't quite name. Walking through a North American prairie, you might feel that something is missing, that the grass is waiting for grazers larger than bison, that the space between trees is sized for creatures that no longer fill it. The silence contains the echo of missing footsteps, the ghost of missing calls, the shadow of missing relationships, but silence, especially the profound silence that follows great transitions, is also creative space. It's in silence that new sounds can emerge, new relationships can develop, new ways of being alive can establish themselves. The post-glacial world, for all its losses, also became the setting for remarkable innovations. The development of agriculture, the evolution of new species adapted to post-ice age conditions, the emergence of human civilizations capable of art and science, and the kind of wondering that allows us to study our own history. Standing today in landscapes that were once buried under miles of ice, listening to the sounds of forest and field and stream, you might still detect, underneath the symphony of established life, the original silence. It's there in the spaces between bird calls, in the moments between waves on post-glacial lakes, in the pause between wind gusts through trees, that are still, in some sense, colonizing territory that ice held for 100,000 years. This silence is not empty or sad. It's expectant, potential, full of possibility. It reminds us that even the most complete transformations leave space for new beginnings, that even the most devastating changes create opportunities for new kinds of beauty, new forms of relationship, new ways of filling the quiet spaces left behind by whatever has passed away. And as we listen to this ancient silence, As we try to understand what it means to live in a world still shaped by the retreat of ice, we might ask, what other great transitions are we living through? What other silences are we creating? What will grow in the quiet spaces we leave behind when our own moment of dominance passes, and the world begins once again the patient work of writing new stories in whatever empty spaces we've created? The ice teaches us that retreating doesn't mean disappearing. That ending doesn't mean concluding. That silence doesn't mean absence. Sometimes silence means possibility. Sometimes it means the world is listening, waiting to hear what wants to be born in the space that's been cleared. What wants to grow in the ground that's been prepared. What wants to sing in the quiet that's been made ready for new songs. In the deep mathematics of orbital mechanics, in the precise gravitational dance between Earth and Sun and Moon, the future is already written. Not the details, not where you'll live, or what you'll dream, or whether the next winter will be harsh, or mild, but the broad strokes. The fundamental rhythm that has governed our planet's climate for the last 2.5 million years. And according to those calculations, if humanity had never existed, if we had never learned to burn fossil fuels and release ancient carbon into the atmosphere, our planet would already be sliding toward the next ice age, the Milankovitch cycle's name. For the Serbian mathematician who first calculated them describe how Earth's orbit around the Sun changes in predictable patterns over tens of thousands of years. The shape of our orbit shifts from nearly circular to more elliptical and back again every 100,000 years. The tilt of our planet's axis wobbles between 22.1 and 24.5 degrees every 41,000 years. The direction our axis points changes every 26,000 years, determining which hemisphere receives more direct sunlight during which seasons. These cycles, subtle as they seem, control the ice ages. When the northern hemisphere receives less summer sunlight due to orbital geometry, snow that falls during winter doesn't completely melt during summer. Year after year, the snow accumulates, compacts into ice, begins to flow under its own weight. Glaciers form in the mountains and spread onto the plains. Ice sheets grow from small beginnings into continent-covering monsters that reshape the world. By the orbital calculations, we're currently past the peak of our interglacial period. The northern hemisphere summer sunlight that melted the last ice sheets has been gradually decreasing for several thousand years. If we follow the pattern of previous interglacials, we should be approaching the slow slide toward the next glaciation. In perhaps 5,000 years, maybe 10,000, certainly within 50,000 years, the ice should begin its return. But we have fundamentally altered the equation. The carbon dioxide we've added to the atmosphere from burning coal and oil and gas, from clearing forests and plowing grasslands, pushed greenhouse gas concentrations to levels not seen since the Pliocene epoch, 3 million years ago, long before ice ages became regular features of Earth's climate. We've added enough warming to potentially delay the next ice age by tens of thousands of years, maybe longer. This might seem like an unqualified good thing. After all, ice ages are catastrophic from a human perspective. They make vast regions uninhabitable, disrupt agriculture, force mass migrations, and have repeatedly pushed our species to the brink of extinction. If we've accidentally prevented the next ice age, Haven't we solved one of the greatest long-term threats to human civilization? But climate systems don't respond to greenhouse gases with simple, linear warming. They respond with complexity, with feedback loops, with sudden shifts between stable states that can happen much faster than the gradual changes that trigger them. And ice, it turns out, has its own ways of responding to warmth that can be more dangerous than the gradual advance of glaciers. Consider what happens when you add heat to a world with massive ice sheets. The ice doesn't just melt gradually from the edges inward. It begins to melt from below as warmer ocean water circulates underneath ice shelves. It develops rivers and lakes on its surface that can suddenly drain through cracks, lubricating the base of glaciers and causing them to slide toward the ocean much faster than expected. It becomes unstable in ways that are difficult to predict and impossible to reverse once they begin. The West Antarctic ice sheet, which contains enough water to raise global sea levels by 12 feet, is already showing signs of instability. Some scientists believe it may have passed a tipping point beyond which its collapse is inevitable. Even if we immediately stopped adding greenhouse gases to the atmosphere, the collapse wouldn't happen overnight. It would take centuries or millennia once it begins. It would continue according to its own internal dynamics rather than our intentions. Greenland's ice sheet, containing enough water to raise sea levels by more than 20 feet, is losing mass at an accelerating rate. During the summer of 2019, 90% of the ice sheet's surface experienced melting, something that had never been observed before in the satellite era. The meltwater doesn't just contribute directly to sea level rise. It also changes the albedo of the ice sheet, making it darker and more likely to absorb heat, which causes more melting, which makes it even darker. But perhaps the most unsettling aspect of our current situation is that we're conducting an unprecedented experiment with our planet's climate system. Ice ages have been the dominant climate state for the last 2.5 million years. The warm interglacials, like the one we're living in, have been brief exceptions, typically lasting 10 to 20,000 years before ice returns. We're now pushing the system into a state that has no analog in the recent geological past. Some climate models suggest that the warming we're causing could persist for tens of thousands of years, long enough to fundamentally alter the orbital relationships that control ice ages. We might be shifting Earth into a different climate regime entirely, one where ice ages are no longer possible, where the great cycles that have governed our planet for millions of years are permanently disrupted. Other models suggest that our warming might be temporary on geological timescales, that eventually natural processes will remove the excess carbon dioxide from the atmosphere, and orbital mechanics will reassert control. In this scenario, the ice will eventually return, but to a world that has been completely transformed by our brief but intense influence on the atmosphere. There's also the possibility of abrupt climate transitions that could bring iceagulic conditions even in a warming world. The shutdown of ocean currents, like the Gulf Stream, could plunge regions into cold that persists for centuries or millennia, even as other parts of the planet continue to warm. Local ice sheets could form and persist in areas that experience sudden cooling, creating a patchy, chaotic climate, unlike anything in the geological record. Perhaps most troubling is the possibility that we're creating conditions for an ice age of a different kind entirely. Instead of gradual cooling triggered by orbital cycles, we might be setting up conditions for rapid cooling triggered by climate system instabilities. Massive volcanic eruptions triggered by the weight of water from melting ice sheets pressing on the Earth's crust could inject enough particles into the atmosphere to cause sudden global cooling. Changes in ocean circulation could redistribute heat in ways that bring ice age conditions to some regions while leaving others warm. The indigenous peoples of the Arctic, whose ancestors survived multiple ice ages, have oral traditions that speak of sudden climate changes, of winters that lasted for years, of ice that advanced and retreated in patterns that don't match our scientific understanding of gradual glacial cycles. Western science has generally dismissed these accounts as mythological, but as we learn more about the potential for abrupt climate transitions, some researchers are beginning to wonder if these stories preserve memories of climate instabilities that our ice core records haven't captured. Standing in our current moment, watching ice sheets melt and weather patterns shift and atmospheric chemistry change at unprecedented rates, we find ourselves in a position that no species has ever occupied. We have become a geological force powerful enough to disrupt the orbital cycles that have controlled our planet's climate for millions of years. We're conducting an experiment with ice and heat and atmospheric chemistry whose outcome we can't predict with certainty. The question that hangs in our warming air is not just whether we can prevent the next ice age, but whether we should. Ice ages, for all their destructive power, have also been engines of evolution, drivers of adaptation, creators of the selective pressures that shaped our own species into what we are today. Without ice ages, would humans have developed the cooperation, the technology, the resilience that allowed us to become a global civilization? And if we succeed in preventing the return of ice, what other cycles are we disrupting? What other natural rhythms that we don't yet understand are we interrupting? What long-term stability are we sacrificing for short-term habitability? The ice ages teach us that our planet's climate is not a stable background against which life happens, but an active participant in the story of life itself. The cycles of ice and warmth have shaped evolution, driven migration, created and destroyed ecosystems, and repeatedly tested the limits of what's possible for complex life on Earth. Now, we find ourselves in the position of potentially ending those cycles, of becoming the authors of our planet's climate future rather than its subjects. Whether this represents wisdom or hubris, salvation or catastrophe, may not be clear for thousands of years, but one thing is certain: the next ice age, whenever and however it comes, will encounter a world profoundly shaped by our brief but intense tenure as a planetary force. And as we contemplate this uncertain future, as we try to understand what it means to have such power over the climate that shaped us, we might ask, in all our efforts to control ice and warmth and the chemistry of the atmosphere, what are we trying to preserve? What do we hope will survive? When our influence on the planet finally ends and natural cycles reassert themselves, the answer, perhaps, lies not in the ice itself, but in what remains when ice is gone. There will come a time, perhaps tomorrow, perhaps in 1,000,000 years, when the last glacier on Earth finally melts, when the last ice sheet slides into the rising sea. When the frozen archives of the polar regions release their final memories into the warming air, what will remain then? What survives when the ice that has shaped our planet for millions of years finally disappears entirely? The question haunts more than climatologists and glaciologists. It reaches into the deepest philosophical territory, into questions about permanence and impermanence, about what we mean when we say something exists, about the relationship between matter and memory, between presence and trace. Start with the most obvious remnants, the landscape itself. Even after every glacier has melted, even after the last ice sheets have disappeared, the Earth will still bear the scars and gifts of their passage. The Great Lakes will remain those massive depressions, carved by ice and filled by its melting. The Finger Lakes of New York, the thousands of kettle ponds across New England, the fjords of Norway and Alaska, of these will persist as testament to the power of ice to reshape the world. The soil of the American Midwest will still be there. That rich agricultural foundation built from the pulverized remnants of the Canadian Shield, ground fine by glaciers and deposited across the continent like a generous gift from the ice ages to future farmers. Every cornfield in Iowa, every wheat field in Kansas will continue to grow in dirt that remembers the weight of ice, even when ice itself has become just a word in old books. But what about more subtle traces? What about the biological legacies, the evolutionary adaptations, the genetic memories that life carries from its long relationship with ice? Consider the polar bear, that magnificent predator, so perfectly adapted to life on sea ice that it seems like a creation of ice itself. If Arctic sea ice disappears entirely, polar bears may go extinct, or they may hybridize with grizzly bears and gradually lose their polar adaptations. But some of their genes will persist in the hybrid populations, carrying forward the molecular innovations that allowed life to thrive in the coldest places on Earth. Arctic plants have developed extraordinary adaptations to survive in permafrost, to photosynthesize during the brief summer growing seasons, to reproduce in conditions that would kill most other plants. As the Arctic warms, these plants may migrate north toward the retreating ice, or they may retreat to high mountain refugia, or they may simply go extinct. But the innovations they represent biochemical solutions to the problem of life in extreme cold. These will remain in the genetic library of Earth, available for rediscovery if ice ever returns. Even more subtle are the cultural legacies, the human memories and knowledge systems that ice helped create. The Inuit languages contain dozens of words for different types of ice, different conditions of snow, different ways that water transforms under extreme cold. If ice disappears entirely, these languages may lose some of their precision, but they will still carry the cognitive frameworks that ice helped shape, the ways of thinking and perceiving that emerged from millennia of life in intimate relationship with frozen water. The stories will remain. Every human culture that has encountered ice has woven it into their mythologies. Norse mythology speaks of Ragnarok, the twilight of the gods that begins with a winter that lasts for years. Hindu cosmology describes cycles of creation and destruction that last for millions of years, ages that end in fire or flood or ice. These stories may outlast the ice that inspired them, carrying forward the human experience of living with forces larger and more powerful than ourselves. But perhaps the most profound legacy of ice lies not in the landscape, or the genes, or the stories, but in consciousness itself. Ice ages didn't just shape the evolution of our bodies, they shaped the evolution of our minds. The cognitive abilities that allowed our ancestors to survive ice ages, the capacity for long-term planning, for cooperation in small groups, for innovation under pressure, for finding meaning in hardship, these became the foundation for everything we consider uniquely human. Art, music, language, technology, science, philosophy, of these emerged. From minds shaped by ice ages, from consciousness that developed in constant awareness of its own fragility, from intelligence that learned to find beauty and meaning in a world that seemed determined to erase it. The cave paintings of Lascaux and Altamira, created by candlelight during the last ice age, represent not just artistic achievement, but cognitive revolution moment, when consciousness became capable of representing itself to itself, of creating meaning that could outlast individual lives. If ice disappears entirely, this ice-forged consciousness will remain. The human capacity for wonder, for questioning, for imagining possibilities beyond immediate experiences. Gifts from the ice ages will persist in every child who looks at the stars and asks where they came from, in every scientist who studies the past to understand the future, in every artist who tries to capture something eternal in temporary materials. The sciences themselves, geology, climatology, paleontology, archaeologies, ways of understanding the world emerged from ice age. Consciousness, from minds that learned to read the deep history of the earth in rocks and bones and layers of sediment. Even if ice disappears, these sciences will continue, carrying forward the ice age gift of seeing deep time, of understanding that the present moment is part of a story that began billions of years ago, and will continue long after we're gone. Mathematics, too, bears the trace of ice. The statistical thinking that allows us to understand probability and uncertainty, the geometric insights that help us navigate space and time, the abstract reasoning that lets us model complex systems. All of these cognitive tools were refined during the ice ages, sharpened by the demands of survival in unpredictable environments where small miscalculations could mean death. But there's another kind of remainder, more subtle and perhaps more important than any of these. In every moment when someone chooses cooperation over competition, when someone shares resources during scarcity, when someone tells a story to comfort a frightened child, when someone tends a fire through a long night, in all of these moments, ice age wisdom persists. The deep knowledge that survival depends not on individual strength, but on collective care, not on dominating nature, but on understanding our place within it, not on avoiding uncertainty, but on learning to thrive within it. This wisdom doesn't require ice to remain valid. It doesn't become obsolete when glaciers melt. If anything, it becomes more necessary as we face new forms of uncertainty, new challenges to survival, new tests of our capacity to adapt and cooperate and find meaning in difficult circumstances. Perhaps this is what will remain when the ice is gone, not just the physical traces and biological legacies and cultural memories, but the capacity itself, capacity to endure, to adapt, to find beauty in harsh conditions, to create meaning in the face of uncertainty, to to care for each other when the world seems indifferent to our survival, standing at the edge of a melting glacier today, watching ancient ice become modern water. Listening to the sounds of a world in transition, you might feel profound sadness for what's being lost. But you might also feel something else: gratitude for what ice has given us. Recognition that its greatest gift was not the ice itself, but what ice made possible: consciousness capable of recognizing loss, the intelligence capable of understanding change, the heart capable of grieving for a world that exists now only in memory and imagination. Ice taught us that nothing lasts forever, that stability is temporary, that change is the only constant. But it also taught us that impermanence doesn't mean meaninglessness, that endings don't negate beginnings, that what remains when something is gone can be more important than what was there in the first place. What remains when the ice is gone? We remain, carrying forward the gifts that ice gave us: the capacity to remember, to wonder, to adapt, to love in the face of loss, to find hope in the space between what was and what might be. We remain not as the conquerors of ice, but as its children, its inheritors, its living legacy. And perhaps that's enough. Perhaps that's everything. Perhaps the greatest achievement of ice was not the landscapes it carved or the species it shaped, but the consciousness it created, consciousness capable of asking what remains, capable of mourning what's lost, capable of imagining what might come next in the end. What remains when the ice is gone is the question itself, and the mind capable of asking it, and the heart capable of caring about the answer. The ice may melt, but the wondering continues. The glaciers may retreat, but the capacity for awe persists. The frozen archives may release their memories into the warming air, but somewhere, someone will remember what it meant to live in a world shaped by ice. And someone will tell the story, and someone will listen, and the greatest legacy of ice's gift of consciousness itself will continue its long journey toward whatever comes next.